Yeah, might as well. And well, it's a few different ways. I mean, you could share your screen and I could just talk about what we're looking at.
Oh, okay.
That's another way of doing it. So if you've got a SEM80 up and running, or could get it up and running, I mean, I can do it too, of course, but if you start a SEM80, we could just sort of walk through.
Emulator. Oh, it's running already. How do I
Okay, you want to share your screen? Okay, so down the bottom there's a bunch of icons. One of them's green, which you just click share screen, and then if you can just you should see a window that has, yeah, that's it, beautiful, perfect.
Hang on, something's not right.
It's right on my screen. I can see it.
There we go.
Yeah. Yep.
Huh? I'm getting crazy characters.
They're weird characters.
I've got APL in the background. That's the problem. There we go. It goes, where is it? This one, dialogue or the usual. Okay, all right.
Yeah, so I can only see your browser, so I can't see anything else. So
you can't see.
I can see Mint. I can see a SEM80. That's, yep.
Okay.
So why aren't we getting errors or anything? Like, yeah.
If I hit Alt or Tab, it'll hang. So I hit Tab, bang.
Okay. Let's stop this. Yeah.
Recycle it.
Okay. Got to get to the bottom of that bug then. Back to IDE or something. I don't know what's going on here.
No, it's not working. Oh, new share.
Yeah, maybe I better do it. Okay.
No good. All right. A few things here. 80. Click. Oh, okay, running.
Yeah, I mean, just do some Mint, like 1 plus dot on yours.
What screen have I got open?
So I can see Mint version 1.1 on the display.
If I type that, you can see that?
Yeah.
Okay.
So that should, yeah, it's good. Plus dot.
Oh, yeah, familiar with that. Yep, that's all good.
Yeah.
And plus comma, I get the hex version.
Yeah, now there's nothing on the stack now, slow down.
Yeah, so I duplicate that. I can multiply it and display it in hex. Yep, that all makes sense to me.
Yep, cool. All right, so let's stop the emulator by using back to IDE.
Back to IDE.
That's at the top right there.
Yep.
Okay, now we've got the source code in front of us. And
very tiny.
Yeah, we can boost that actually under settings. See that on the left-hand side, down the very bottom of those gray buttons, right? Last one. Keep going. Yep. Click that. Now use font size and boost it to the next size up. Anyway, medium I think is pretty good. Yeah, I can see that pretty clearly. And you can change the light if you like. You know, and you can change the wide too. That might be a good idea.
Okay.
And that's my general setup anyway. So go back now to workspace, the first one. All right. So what we're looking at here is that's the program you run. So let's just talk about this. The first line obviously is the emulator, which you already know about from everything else that we've done with this. And so we don't really need to go into the settings for that, I don't think, but you can go in there, might as well. Yeah, might as well for other people who might be watching this video. Yeah, okay, so CPU, this sets up a memory map between, so the ROM is from 0 to 800 more or less, just before, so that's 2K. The whole of Mint has to be able to operate in that space. Everything from 800 or 2K upwards to 64K is RAM.
That's not real. That's not a real tech one there.
No, but and in reality, you very rarely bump into these. I don't even know what these settings really. I don't think you even need to worry about them, to be honest. serial 6850 that you definitely need to turn on, and serial data, and specify the ports that get used, and
So
that's
in this case, it'll be bit bang in this part here.
yeah. And so, but we will be not bit bagging. So,
No.
but you would be with the Tech One. So this is more like an RC 2040. Was it RC 2014 type of system where you've got a 6850 and all that stuff, but you can do it with the Tech.
Can I ask you, the 6850 is not far away from working. Craig's got one, and my Techopus is actually working in his hands as well. There's another revision coming out. In fact, he's got the 9511 GPU working as well now.
Fantastic.
Yes, it's becoming a polished project, and his hand is amazing. So this will be relevant again.
It'll all be relevant for once we've got a sort of like a Tech configuration that is like that, and he's already been working on that. I haven't been doing any hardware, so that's really the big
You love not doing hardware. That's
the minute I became able to do software, I never went back to hardware. So my knowledge is a little bit sketchier than most other people with regard to electronics these days. I haven't thought about it a lot since in 40 years. So that's one of the reasons. So anyway, and there's a serial interrupt setting. So that causes,
what's that?
That causes, you don't need to worry about it with Mint.
This is a directive.
Again, it's just saying that it's a true or false flag, I think, to say that this is interrupt driven. So it means if there's serial, then something will trigger on 38H. But to be honest, I don't think we're using any of that. So you can kind of ignore it. So yeah, okay, terminal caps. No, yeah, so I guess that could force you to. I suppose that would be useful for uppercase only. Anyway, going back to the main file. All right. So we have two things. Yeah. So two things. We include constants, and then we include the serial. Craig wrote this file completely. So let's look at constants first.
That one there.
Constants SM.
That one there. Oh wow. Right.
Okay. It's a little bit of a grab bag because you can see there's some if statements and so on. But basically, we turn on.
Sorry, John, is this actually assembly or this is just...
Yes, it is.
It is assembly, okay.
But they're kind of at the directive level. They don't consume any bytes. They're not assembling to something. They're just constants.
Right.
So constants are used by the assembler, but they don't take any space.
They're inserted at time of compiling, right.
Yeah, they're part of the compilation or assembly.
Okay.
So Tech 1 is a flag. So EQU just means the symbol Tech 1 equals 1, and the other symbol RC 2014 equals 0.
You can't have both, obviously.
Yeah, we're just treating those as flags. So it's just to say this is a Tech 1. This is not an RC 2014. And you can see if statements through the code. If RC 2014, then do this code. If Tech, then do that code, right? So what it's saying is these constants are going to be different. Yeah, it's just because there's memory addresses are different. See where the ROM starts at 8,000, for example?
Really high.
Yeah, whereas in the Tech one, it starts at 0.
Yeah.
So that's all that's happening there is it's a file that can serve to turn on the RC 2014. So that's mainly for Ken.
There's even Southern Cross in here as well.
Yeah, that's right. And this area would get expanded with more constants and so on
lovely.
in the future, but let's not worry about it too much. And then just go back to the main file again. The second include is IO serial SM, and this is definitely this is Craig's area. And again, you can sort of see there's if it's a bit bang, I don't know where bit bang got defined, to be honest, in that piece of code. But if it's Tech 1, if it's bit bang, then do set up some constants, and otherwise you do something else. If it's a 6850
here.
Yes, there's an else in this particular case. Now, I'm not an expert in this file, but basically everything here gets assembled from 0 location in the ROM all the way up to hex 100. So it's the first 256 bytes of the ROM.
How did you deduce that up to the first 100? Does it say that here somewhere?
It may not say it on this file, but it will say it in the next file.
Okay.
So maybe we can have a look. But if you scroll down, I mean, I know that Craig has been squeezing different routines in here and keeping it below that. Yeah, you might see origin ROM start. Then you see these are locations of the restart addresses.
These are interrupt positions, are they? Vectors,
yeah, software interrupts, and that's an interrupt. 38 is the maskable interrupt, whereas 66 is the non-maskable interrupt. I assume that's been.
I'm very shallow on interrupt technology at this stage, but I kind of understand, but no depth at all. Sorry.
Well, yeah. Well, the main you get the basic idea. It forces the CPU to do a subroutine call. Yeah. And it saves its current location on the stack.
Yep.
And then it goes off somewhere, and then you can just return from it. And you use RTI rather than RET. You use RETI. I'm not completely 100% clear on all this, but it makes sure it ensures that the internal state of the CPU doesn't get screwed up.
Okay.
But anyway, and then he's also put it, and we might as well say what else. So there's not much going on in those restart instructions.
Software go back up the top. This what are all these here again? Sorry, these are just equates.
Yeah. So
this means that. That means that. It's substitution, right?
So they're all equates. So they're just simply saying, in other languages they would just be an equals symbol.
Okay.
And so these are all stuff that is to do with the bit banging area. I don't know anything about it. So you talk to Craig. You talk to Craig about all this. Don't ask me. and then if you keep going down, okay. If Tech 1, so the key buff, scan, display. These are the ports.
These are ancient. These have been around forever.
Yeah. So these are the ports, the Tech 1 ports, and you can see the Southern Cross has got different ports. And they're similar but different.
They're a little bit higher up.
Yeah. And this is the point about Southern Cross.
When you drive, when you want a keyboard buffer, you go to 00, and there's a byte sitting in there from the keyboard.
Yeah.
So that special chip that scans the hex pad, that dumps into there, does it?
Yeah.
Oh, this chip here, the 74.
923.
923. That's got an NMI.
Yeah.
Why do I keep doing that?
I don't know. Sorry. Can you? Because it's going backwards to maybe what sort of computer are you using here? Is it Windows machine, right? Okay.
Windows, yeah.
Can your mouse wheel do the job? I don't know.
Wheel works.
Is it going backwards? Seems
backwards, forwards, yep.
Okay. All right. Okay. So anyway, it's got a lot to do with the way. Anyway, so these are all details. Let's just put it that way. Because the way I wrote the keyboard input, it would trigger a non-maskable interrupt at 66, and it would read in that port and then store the value in a register, the I register. Like that's what I did.
Is that a mint thing you're talking about now, or the monitor?
No, the monitor. So this keyboard and stuff is basically not used by Mint, but it's programmable by Mint. So you could write a monitor in Mint, which would be a really good project, would be to make a useful program like a monitor, but write it in Mint rather than assembly language.
When you switch on the Mint on the Tech 1, the lights are off, the keyboard's dead. It's like there's no life until you connect to the terminal. Yep,
that's right. And so that's the only thing that Mint knows about is the terminal, the bit bang terminal or the 6850 terminal. That's all it knows. Yeah. But it doesn't mean that it couldn't directly access the display, just like those examples we did, Craig and I did for the Tech 1, where we, wrote code to scan the displays.
I thoroughly read those. Yep.
Yeah, so we've got scan and we've got display, the two ports, two latches, and we can control those. And then we've got, one of the bits of anyway, so so that was, so you've been through that. So let's just go, let's sort of just scroll to the end. I don't think there's a lot more we can learn from this because it's all getting into the bit bang stuff, and we'd have to get Craig to kind of explain the code. Okay, that's worth looking at. Okay, so yeah, when you hit reset, it jumps to the symbol reset. So you could probably look for that. It's probably in this file, I'm not sure. And maybe towards the bottom. You can see all of that's bit bang routines.
Oh.
There we go. So it jumps to here. And it just does.
Geez.
What's going on?
Sorry. Here we
you
go.
just click in the click in. You click it, or does it jump around when you click on it?
It jumped around with.
Okay.
Don't
know what's going on. Stack. Yeah. Okay. We set up the stack. We set up HL with, I don't know, int return. Not sure what that. Oh, that's an address, and then we store that into some memory locations that have been defined.
So whatever that is goes into here, and that goes into here, and then that goes into one of these. Yeah,
yeah. And honestly, I'm not completely sure whether this is 100% useful, but basically it means that we can, it has a little interrupt table, and so it could be changed at runtime. Yeah, well, it looks like it's just, look, I think I wrote this code, so that's why I should know the answer, but basically it's just jamming this address int_rent into RST08, and that must be in RAM. Like I think there's
duplicating them into all of these positions.
Yeah. Oh. So it's because it's in RAM. So you want to understand it, go to the ram.asm file. Yep. And there they are. And they're just addresses that
this one?
And it's a table, and it's basically saying define 2 bytes and call it RST08, and then RST10. It's just basically it's just a way to allocate space, and so it's just basically a table of words or addresses.
Can I ask a question?
Yep.
When you do a DS, does that mean you push 2 byte spaces in the address range before you start the next opcode?
It is basically telling the assembler to just jump 2 locations forward
and leave that as a gap.
That's right. So that's right. But it doesn't. In this case, we're not initializing it in any way. We're just simply saying that it's going to have the name.
That does my head in. I'm always thinking that assembler is hard compiling everything that comes across, and here we're compiling empty spaces.
Yeah. All we're doing is we're basically giving these labels on the left an address value, and that's all we're doing. We're not assigning.
Why didn't we just wrap brackets around it? Just call it when we need it.
What do you mean wrap brackets around it?
Well,
it's just all I'm doing here is it's a symbol. That's all. Symbols are more useful than addresses.
This is a label because there's a dot there, right?
Yes. So it's a label. It's a label.
Label to that, but this.
I don't know what's going on.
But this is actually somewhere else, defined by that previous file.
Yeah. So this is basically okay. Go to the top of this file. Basically, go to the top. Yep. It says the origin of this file is the start of the RAM. So basically 800, and then it's saying allocate some memory that is the size of the text input buffer. I told you about the text input buffer before. That's where all the keys get typed when you're entering things. Okay, so the tib size is specified in a constant, but it's in the main mint asm file.
This is a now, is it? Text input buffer.
Yeah. So we're talking about these are locations used by Mint. So the tib is the text input buffer. I call it tib because that's what they call it in Forth as well. And I've allocated a block of memory which is tib size. I can't tell you how big it is. I think it's 100 hex. Then I've got, after that, I declare immediately after it some memory, which is the return stack, which is the R size. So R size is whatever the size I've allocated for the return stack, which again is some value like, 100 hex. I can't remember. We'll have to go and have a look in Mint SM to see what it is. And so that pushes the assembler to now say that R stack is at the end of this block of memory that is R size. And the reason why it's at the end is because you know how stacks grow down rather than up, right?
Okay. So they don't collide with the program then.
Yeah. And in fact, what will happen is if you keep pushing stuff, it'll eventually collide with the tib and start overriding the tib, the text input buffer, but it'll eventually start overriding the ROM. And that's no big deal, right? So it can't really do any damage to the RAM because it's going to keep growing down until it hits the ROM, which is just ahead of this RAM start business.
Now, how do we know that this R stack is at the bottom? How did we push it there?
How do you know it's at the bottom?
We defined it somewhere else, did we?
What do you mean is it at the bottom?
Yeah,
so we've got R size and then we've got R stack. So R stack is the address after we've allocated the size.
Okay.
So, in other words, the address now, let's imagine R size is 100 hex. Imagine that tib size is 100 hex. Then at 200 hex, R stack will equal 200 hex because it's just occurred after two data defined space operators.
This group here is taken sequentially when it's compiled.
Yep.
Okay.
So it's working its way down. It says allocate 100 hex, allocate 100 hex. Now R stack knows that it's basically 800 hex, which is the start of RAM, plus 200 hex. So that's like A00 is where R stack starts. And then we allocate another D size, which I think is 100 hex as well. So then after that, we say D stack.
Sorry, what does D size do?
This is the data stack size.
Oh, data.
Because we have two stacks in Mint.
Okay.
So, yeah. And then D stack starts at the end.
The internal stacks for the mechanism of
this
fourth Mint thing. Gotcha.
That's right. So we have two stacks. One of them you're very familiar with because it's the one you push the data onto, the parameters, called the data stack or the parameter stack. And the return stack is more familiar. It's like the machine code stack. It's mainly used for return
What
address.
about the real stack, SP, that's part of the CPU? Is that part of it?
Well, yes. Let me just explain.
That's a physical stack as opposed to a virtual stack.
Yeah, well, the bit that's interesting about Mint, and this is following in the tradition of Z80 fourths, is that the data stack is so important that we actually use the stack pointer, the machine code stack pointer, as the pointer to the data stack. So we don't use the Z80 stack pointer for storing return addresses for subroutines. We do something different. Okay, so what I'm getting at is pushing and popping to the stack in Mint or in Forth is so important that we don't want to have to use HL or IX or IY. It's just way too slow. But if you push something on using SP and you just go push BC onto the stack using the normal return stack, then we're using the return stack as a data stack, and we need to create a virtual return stack for, otherwise we can't do subroutines, right? So in fact, the whole machine code of Mint looks a bit different to a normal machine code program because we don't use the stack in the same way. And it does your head on,
That's smart. Because they overlap, so you might as well make them efficiently one sort of thing.
Yeah, and it's just because of the Z80 doesn't have very efficient 16-bit read and write operations, which means that everything is done as 8-bit chunks, and you can end up spending like 40 cycles just reading and writing stuff. it's very slow. So whereas to push something on a stack is just 10. And so that means that if you're running at a 1 megahertz, that's like 10 microsecond, 10 cycles of, 10 cycles. So it would be something like 10 microseconds to push
Pretty
something.
slow in computer talk.
Yeah, well, Z80 is not an efficient microprocessor. That's
No,
one thing.
but it's a fun one at that.
That's a funny thing. I don't know why I still like it. I know there are better ones, but there's something about familiarity as well. I know it better than anything else.
Yeah.
So there's also a loop stack, which you might have heard of, as I talked about. So loops are handled using a third stack. And this is a bit of an unusual idea, which I learnt from Peter Jakaki from the Z80, from the fourth 2020 group. In his implementation, he deviates slightly from traditional fourth and uses this additional stack as a way of removing the need to compile the stack, which is something you have to do in fourth. Fourth is a compiler, whereas Mint is 100% interpreter. So I just didn't want to have to compile jumps and do all sorts of stuff like that, like you have to do in classic fourth. But Peter never had that problem with his fourth because he used a third stack, which is called the loop stack. So that's
don't we refer to Mint as a compiler because it does everything straight away, or is that just a mishmash?
Interpreter. It's an interpreter. Yeah. There's a difference. An interpreter is something where the source code is the object code, right? There's no difference. You execute your source code. But fourth, for example, is both interpreter and compiler because it reads in words and then automatically compiles them. And in the process of converting them from source code that you're typing in to compiled, it becomes much faster because it's getting rid of some of the overhead of the interpreter. So while fourth is not as fast as machine code, it's considerably faster than interpreted languages. Mint, on the other hand, is pretty damn fast for an interpreter if you compared it against, say, BASIC or other interpreted languages. And that's because its syntax is so minimal that we can parse and execute Mint statements very, very quickly. So it's one of the faster interpreters, in my opinion. I mean, I'd have to do some benchmarks to prove this, but it's very, very lightweight, and we sort of try to optimize it to be very fast. And this is an area that Ken Boak was very helpful. He would go over and analyze things and try and shave cycles here and there. And we got some really good performance out of Mint, but it's always going to be slower than a compiler, and it's always going to be slower than an assembler. Just because interpreters.
We made that sacrifice to save space as well.
To save space and for it to be interactive, because you can talk to Mint in a way that you can't talk to the Z80. You have to burn to a ROM, so you can't really talk to the Z80, right? As you can't talk to the Tech One, you have to provide it with a ROM, and that's it. The program has been assembled, and then you drop a ROM into the ROM slot and then hit the reset button. But with Mint, you can just go, hello, let's start programming, and you can actually keep programming on the Tech One.
Oh, that's awesome.
And building up stuff in memory. Eventually you'll want to copy that somehow. We still have to work out how to make that
Control L, just capture a file.
yeah, you can do that with the terminal, and that's pretty much what Craig was doing as well. So the interaction with the terminal is the really new idea that interpreters give you that compilers and assemblers don't give you. And we could keep going with this. Like Mint could be then used to compile. It could be used to compile code. So we could say, instead of interpreting this code, why don't you generate some Z80 opcodes into this location in memory? Then it would be acting more like an assembler. And we could definitely do that. I haven't done it yet because not completely sure how big a gain we'd make, but it could be quite significant. So it's something to think about as a future direction, is to make a full compiler out of
That'll
Mint.
become a serious tool if it could do that.
Yeah, absolutely. And people might start paying attention to it too on that basis, because it would actually produce faster, nearly fast enough code. It'll still have some overheads, no doubt, because the stack and all that stuff. But
The Mint could rewrite itself and compile itself.
Yeah, yeah, it
Let
could.
me go again. Jeez.
Although I reckon it would be very hard to beat my Z80
Of course,
handwritten.
you're the best, mate.
Oh yeah, of course, I'm the best. No, that's not the reason. The reason is just because compilers, like the C compiler, just cannot compete against
Yeah, you guys have
handwritten
thoroughly,
SQL.
yeah,
Yeah,
you guys have thoroughly thought through the speed, shaving speed, into putting speed in the system by shaving off redundancy and having a different approach. Like you said, you're just gonna,
yeah,
I just cut you off there. You're gonna say something about the way the stack is used and all the.
yeah. And yeah, I think we've got as good a model as we can for the Z80. But you know, there's always new paths to go down, and we might still. But the main point is we just don't want to. Whatever we do doesn't want to be slower than what we've got now. You know,
Indeed.
and if we can get better, it'll be better. But we'll see what.
And still running 2K. There you go.
Yeah, and
That's crazy.
That's the bit I'm most proud of. Although most people go, "Why did you do that? Why do you just use more ROM?" I go, "Because I want to do it in 2K because Tech One has only had 2K." And to me, 2K is still big. Like for most, when I first started programming, you know, when I was first designing the Tech One or the prototypes, you know, I was looking at 256 byte memory and stuff. It was just that the 6116 came along in the years that I was actually looking at chips and went, oh, that chip, you know, and then we got 2K. And then also the ROMs, like the first ROM I was using was a 2708, which was very hard to program and it was only 1K.
Tiny.
And then the 2716 came along and it was easy to program comparatively. So, you know, it was just a luck that we got 2K of ROM and 2K of RAM. If you look at any of the computers from the previous, like the Electronics Australia era computers, they all had much smaller memories.
You know.
This
2K 2x2 is such an elegant size.
Yeah, I like it. It's almost big enough. And with Mint, it is big enough for a lot of non-trivial work. And don't forget also like the ZX80 and the ZX81, they operated out like with 1K of memory. You'd buy it and it would only have 1K. You'd have to get a 16K expander.
There's a chess game that runs in 1K. It's crazy.
Yeah, you can do it. So anyway, so let's just keep going. So then we're looking at opcodes. There's going to be a reason for that. I think that's a table that we copy some code down to. So you can see we've allocated 80 hex. And then we've got control codes and we've got alt codes in a table of 80 hex as well. So this is where I'm going to have to, it's gone a little bit out of my head, this, so we'll come back to that, whether that's being actively used. I think it is. We're copying stuff from the ROM into the RAM, but I need to go back and have a look at the implementation. So then we've got some variables, mint vars, and we've got then they don't look very defined, but I think they are defined in the other file. Then we've got v loop stack pointer. So that's the variable which contains the loop stacks pointer. So
is that different from this one?
Yeah, it is, because this is where we store the actual pointer, because there's no register. It's being stored in memory. So that's the memory location for the variable stack pointer, the loop stack pointer, which is the third stack pointer. And so that's okay. So and then byte mode is actually used by the array. So we want to switch between word mode and byte mode when we're doing arrays. So when we define an array, we either use a square bracket or we use a slash square bracket, and that just simply sets the mode so that then it knows that the numbers you're typing in should be interpreted as byte values or as word values. It's just, that's what that's for. TB pointer, that's text buffer pointer. So that is pointing into the tib, which is the text buffer. And this is the pointer that points to the tib. And you can access this from your programs. Okay, so then these are vectors, this restart 08, 10, and so on. I don't think it's being used properly. So let's skip all of these variables, as in I don't think they're being fully utilized. That board value is one that Craig is using for his bit banging routines. And yeah, if you look a bit further, and yeah, some of those, I think you can ignore the rest. Okay, get CVec and put CVec are get character and put character pointers. So they point to the routines that are needed for get character and put character. And those are the only two routines that Mint needs to operate, because that means it can talk to the terminal. It doesn't care about the 7-segment displays. It doesn't care about the keypad. It only cares about talking to the serial line. And that's what it's for. Okay, so scrolling down a bit further, you're seeing the variables. Yeah, and you would be aware of these alt vars because they are /A/B/C/D, etc. And so if you wanted to know what A is, it's the equivalent of the starting point of the stack pointer. So this is the starting point of the data stack pointer. So it's the start of memory for the stack pointer. It gets initialized with dstack, the symbol dstack, which is the start of the stack, and it grows down from there. Base 16, you know this one. So /B is the base. You discovered this the other day. So that's the base. Yep. And so that's the base. Tib pointer is giving you a pointer to the tib. I've got to work out what the difference between TB pointer and tib pointer is. I think TB pointer, the one on line 26, is to do with tests. So you can ignore the other one. That one you can ignore. I'm using that to run my unit tests, but it's not important to Mint. Whereas tib pointer, this is the one this is the one you shouldn't ignore. This is the one that gives you an idea of where in the buffer you are currently pointing. But the one on 26, ignore it. So only pay attention to the one on 45. Okay.
Yep.
So /C is the way you could get access to it.
And what to do again?
It tells you where in the text input buffer is the current, is the last character that you've typed, basically. So it's a piece of memory that as you type, the character is going to get put into the tib at the pointer location. Then the pointer is then going to be increased by 1. So you can imagine as you type hello, it's just going to drop characters into the tib at HELLO, and tib pointer represents the end of the input in a sense. It represents the last thing that's been entered. NS you can ignore. That's an experimental thing to do with namespaces. I won't go into namespaces. It's just a way of getting more variables in the system. But we can ignore that. So last def is the address of the last defined command. So if you did a colon word, semicolon, it would be defined, its address would be stored at last def. Yeah, so if you did that, that's exactly it. Okay, and there's a couple of others. There's /F, doesn't look like it's defined for anything meaningful. Alt page, I have to go back and have a look at what that is for. And heap pointer is important. So /H, you already know about. this is the location on the heap that has the last thing that was allocated on the
Oh,
heap.
you explained a little bit about this. Yeah, I captured that in your
Yeah.
notes. Yeah, interesting.
So this is how we do dynamic memory allocation, because the heap is like a bit like a stack, but it grows upwards and it consumes all the available RAM eventually. So this is how you can store strings, it's how you can store arrays, and it's even where we store the definitions for the commands. So the functions, or whatever you want to call them, the defs, yeah. So that gives you an idea of most of the RAM use, but if you go down a bit further, you can see that, keep going. Yeah, see, the last thing we've defined in that is heap, right? So the very last thing is heap. Wow, that's annoying. We're going to have a big problem in that other file if this keeps happening. So anyway, heap is allocated, the heap pointer is assigned to the address heap, which will be located.
There's nothing down here, it's empty.
Yeah, because we're going to start, this is RAM, right? Don't forget we don't.
Oh.
Yes, this is the start of the free memory. And we're just going to keep allocating and consuming this memory using the heap pointer /h is going to keep growing. Every time we define a word, then /h goes up. Each time we define an array, /h goes up. If you want to free that memory, then all you have to do is reduce /h, the heap pointer, and it will overwrite some of that memory. You know, you have to be careful when you do that. So you can reduce the heap use as well as increase it by manipulating that pointer called /h.
You have to keep it at record of counting up and down where you're going. Then you crash into things. You overwrite stuff.
Well, you won't overwrite them unless you have a policy of freeing up some of that space. So anytime you start reducing, then yeah, you'll end up growing again and overriding. But usually you'll be saying, I'm never going to use that array ever again. So let's free that memory. And so let's reduce the heap pointer /h by the size of the array, and then I can allocate a new array. So it requires management. You have to write programs that don't clobber it, that don't end up clobbering yourself. You know, you have to know what you're doing, but it's a lot like a stack.
Yeah. You consider an array like multi-use, whereas a stack is a single use.
Well, we use the heap. Yeah, I don't know really what. Well, I mean, look, a stack is something.
So once you call a stack, you destroyed its contents, and the answer might put the value back on the stack again that you retrieve later. But with a heap, it kind of lingers.
Yeah, okay. I guess
working that parcel of data over and over and over.
Yeah, I guess the point is this is very commonly used in C programming and most languages. The stack is used for passing parameters to subroutines and for storing the return address and coming back. And it's very dynamic in the sense that you're pushing stuff and you're popping stuff and it's continuously changing. Whereas the heap is a place where you put long-living things, data structures that you want to have last.
I've got an extended question then to that effect, because the telescope project will have to have a Cordic sub function. That means I should use an array to put the Cordic values from 0 to 45 degrees and then keep recycling that information every time I need to calculate an angle's sine or cosine function.
So you want to create a constant array that doesn't change. So you define it early in your program. Define it there. And leave it on the heap. And because you're not going to be freeing up stuff at the bottom part of the heap, you know, you can put all your constants there. So you've got lookup tables and other things. You would define them early on in the program and then just keep using them. And,
when I attempt this, I'm sure I'm going to fail 25 times. I'll be calling on you.
Of course, we'll work. Yeah, these are tough things. So you know.
Yeah. Once they're done, they're learned. Then it's easy failing. Yeah.
But definitely, you want to store lookup tables as arrays, And this is an example where you'd store them as 16-bit values, more likely than as bytes, because they're going to be like that. And those are the two types of arrays that we easily can access anyway. And you might want to store them as 32-bit values. Who knows? So we'll need to work out how to juggle that a little. But you can see that that this is the heap is the way you do arrays, and it's a very simple process. It's a very simple mechanism. So it's easy to understand, but it's not very advanced. It's not very high level. Still got to think in a low level way, like machine code kind of way of thinking. Okay, so let's go back to the Tech1 main file. And all right, so now the interesting thing that happens here is that, okay, it's done these two things, define the constants, define the IO serial, then it does a jump, but you don't know where it's jumping to, but I can tell you it's jumping forward into the start of the program. So what this is it's assembling now at 100. This actual location here is 100 hex, 100 hex. And that is, you would have got here after the IO serial initialization code had run. And it's going to now jump somewhere into the mint assemb file. It's going to look for a symbol called start, and it's going to jump there. So that's what this function does. Not function, operation does, is it jumps to the start of mint. Is
that necessary? You have to have at least one jump to get out of this.
Yeah, because mint doesn't start at 100. Mint starts at some location deeper in. And it's all just got to do with because we want to allocate tables and do all sorts of stuff. So we'll get to the mint assemb now. Might as well just jump
to this one.
Yeah, might as well open that one. This is the longest file.
This one.
Yep. This one we're going to screw up all the time with that funny scroll you've got. So I don't know what's going on with that. But okay, so now let's just look. We'll start from the very beginning. These are constants. So you were wanting to know how big the stack was before and how big the return stack was before. And I said 100 hex. Well, in fact, it's 80. So the return stack is 80. The data stack is 80 hex.
They're pretty small.
Yeah, because they don't need to be big. And the loop stack is 80. Don't know how big that should be. Probably can be less. The size of the tib is 256 bytes, which makes sense because, go ahead.
So if you're running out of ROM space, you kind of crunch these up a bit.
No, this is all RAM. These are all RAM locations.
Ah, RAM, okay.
Yeah. So we're talking about the data stack, the return stack, the loop stack. They're all 80 hex, and which is 128 bytes in decimal each. Then we get to the TIB, the text input buffer, which is 100 hex, which is 256 bytes long. That's because a typical input that a user might put in, it's probably quite easy if you imagine someone typing in 256 characters, but beyond that, they're going to
How many bytes is it again?
256 bytes.
Oh, right. One of those, okay.
Yeah. And that's just saying that that's a reasonable input line. The longest line you can imagine would be 256 bytes. Yeah, and then true and false have been defined in Mint's versions of true and false are different from other languages. False is the same, it's 0, but true is +1, not FF, which is the way it is in C and other programming languages. We went for +1 for truth. And that's because, in C, it helps with certain things to be able to have that like that. But I'll explain how our how our if statement works later. And it's
the true and false, is that a Mint request or a assembler thing?
It's actually assembler, but sometimes we need to give Mint true and false values. So I've just defined them here. So these are mint true and mint false. Assembler doesn't know about true and false. It doesn't even have a concept. But Mint cares about the true value that you need to use in conditional code, like if statements, has to be 1 for it to work,
Oh,
not FF or any other value.
0 open bracket, close bracket, or 1 open, for looping.
Exactly. And you know how it works. It's using the loop mechanism. It's a little bit of a shortcut. I sometimes think it wasn't necessarily the smartest decision, but it was done early on in the design of Mint. And it has that elegance of meaning there's fewer commands to worry about because loops and if statements are implemented the same way. I did then, of course, implement an else, as I told you about, which is the second set of parentheses, which means we extended the if statement to a slightly more powerful
you just have a second set of brackets, so you just
that's right. Yeah,
bang bang like that.
Exactly.
And no space.
Yeah, and no space. And obviously the documentation that you found wasn't up to date about that. So slash parentheses doesn't work anymore. But I don't know what it does now. It might be doing something else. Empty, I'm not completely sure what empty is, but it's referring to it could be an empty string. I just can't quite remember what it stands for. Oh, I know what it is. I think it means an empty macro. It means that most macros, when you hit when you hit the control key and a letter, it will fire off a macro. And a macro in this case just means a command that is triggered by the interpreter, not one that is executed. If that makes sense.
Can you just repeat that again? Sorry.
So a macro is something that gets triggered by a control key. So I'll give you an example. Control H backspaces over the last character. And Control E edits.
There's a couple of these. Control L, Control P, Control H.
Exactly. And you asked the question, why did I double up on Control H and backspace? And that's because you probably don't know this, but on terminals, when you hit the backspace, it actually triggers a Control H. So Control H is a well-known backspace operation. It's part of ASCII. You can look up the definition in the ASCII table. You'll see a control code, and it's called at H. So A is ASCII. So first off, you have ASCII 0, which is null, right? Then you have Control A, and that is ASCII 1. Control B is ASCII 2. Control C is ASCII 3. If you get up to Control M, then it's ASCII 13, and that is also carriage return, the ASCII for carriage return.
That's a duplication. Gotcha.
Well, no, it's the same. It's literally the same character. So, so you can always hit carriage return by just doing Control M with a terminal, and it will work.
So the effort of pressing two keys together is actually an anomaly of the keyboard's hardware that generates one output code.
Yeah, it does. And it's history. I think it's caused by IBM or somebody who said that we should have a carriage return and a line feed. Whereas in Linux, you only need to have a line feed. And it's a long history of these kinds of things. And so anyway,
and a macro then triggers the subroutine of a little bit of assembler code and then does it. Or does it actually run a mint string?
It actually runs a mint string. So
all
of those macros, and I'm using the word macro. I'm going to confuse you in a minute because assembly also has macros.
Of course.
But this is the word I'm using. Yeah, right. So these are control key routines, and they're all written in Mint.
Well, that's efficient. Why waste space? It's like you could substitute a lot of the internal things this way.
Yeah, so it does save space.
It slows it down if you use too much Mint. So there's a balance between assembler and Mint.
Exactly. So you can see that like the backspace key is actually controlled by Mint. And I might even be able to point you in the direction of the code.
A tiny job, you might as well.
Yeah. So what have we got? It's called, I thought I put it in a file somewhere, but I'm maybe I think it must. I've got to include further down, and you'll see where to go. And I just can't remember which files we're looking at. So
You're
anyway,
looking
let's just
for a further example, were you?
yeah, I'm going to show you all the examples of the control keys, but we'll do it later. We'll do it later because they might be in this file. I just can't remember.
I documented your control keys as well. Control E, Control J.
Yeah. There's a few.
Control L, list definitions.
Yep.
Can you see what I'm looking at now on the screen?
Yep, I can see it. Yep. The table, your
Yeah.
spreadsheet. Yeah.
What else we
So
got?
so those are
couple.
those are all written in Mint, and they're all triggered by a control key sequence. And if the letter has empty, which brings us back to what empty is, then it knows not that there's nothing being defined for that control key. So if you do control U or something, it will probably look up the location for U and find it's got an empty in it. And if it's empty, it won't execute. Okay. Because most of the keys don't do anything. There's only like 6 or 7 keys that actually do anything. They could all be defined to do something, but we just don't have enough room.
That would be interesting.
Okay, yeah, it would be good.
Hard though.
We're running out of in 2K. We can't have everything. So in theory, you could make it something that you could have user control over or something like that. But anyway, so in theory, you should be able to add your own control key shortcuts into.
And you'll show me how. Yes.
Yeah. At the moment, it might not be able to do it. It might be a bit too hardwired, but you can. Yeah. I'll show you the mechanism. We can always change the ROM. That's the point. Anyway, let's scroll down and talk about real macros now, because I just confused you by using the word macro, but that was referring to control keys. Now I'm going to talk about that the assembler actually has a few macros, and they're really not.
And they're specific to Z80.com.
Yeah, they are. Okay. So we've got lit data and a length.
What's this one here, John? Mint data file.
We're using it for something. You can see that it's probably the size of the table.
2 times 2, right, over and over, right.
I think it's mainly for commands like A to Z.
It's a reserve base thing, gotcha.
Yeah. So it's a constant. Look, I don't think we need to know about. Yeah, I don't think we need to go into those macros at the moment. They're basically. We can talk about these. These I put these in as a way to compress the command ROMs, the command tables. So this is a way of compressing the command tables. I'll show you what they do in a minute, because they're probably just going to be confusing until you see. But what I did was I needed to squeeze we've got these tables which have these sort of ways of mapping from, well, what does what does asterisk mean? And then you look it up in an ASCII table, and you'd see the ASCII for asterisk is actually attached to the multiply routine, or the ASCII for plus is attached to the plus routine. I don't think you need to look at this. Just go back, just listen, and we'll talk about the ASCII table in general. What I'm saying is we have a table, which means that you can, when you type in 1, 1 plus, it's going to know what to do with the numbers, and it's going to know what to do with the plus character. So it's all driven by tables. But tables take space. I mean, your lookup table, for example, imagine if your lookup table that you were talking about before had a lot of zeros in it, or it had a lot of or it has a lot of repeated stuff in it. Yeah. Then these macros are designed to define the table in such a way as to compress it a bit. I'll show you how it works later, though. So, okay, scroll down a bit further. We get to org, origin.
What's this here, LN?
It's a parameter that's being passed in, but I'm telling you, let's not talk about this now, because it's too advanced. Okay, so we just talk about that later. That's compression. You don't need to compress stuff if you've got lots of space, right? So this is just to do with compression.
How far do I go down? Oh, look.
Line 41. Line 41. This is exactly where we want to be. Okay. 41. What it's saying is that at the location start of ROM, which is 0, plus 180 hex is where we're going to start putting Mint. So when I said that Craig actually has control over the bottom 100 hex, I think it's actually 180 hex. I forgot. We actually needed some more space for that bit bang, so we gave him 180 hex bytes to work with, and that's like 256 plus 128, you know. And then I'm starting to allocate some control key things in the next part. So you can see there's no code here. This is all data. As in,
the backspace is all that.
It's min code, yeah. It's a string, basically, okay? Yeah. So we're saying define bytes which have got the following values. There's 2 slashes, and the reason for the 2 slashes is I'm just trying to do a single slash, but because we're inside a string, and the slash is already being used as a way of expressing control codes and stuff like that. In order to put a single slash into your string, you have to escape it with another slash. So wherever you see slash, you should read that in Mint as a single slash. Does that make sense?
Yes, it does.
Yeah, okay. So that's obviously this is the backspace operation. So this is Control H, right? Backspace, which if you went to the ASCII table right now, that thing you had before in the browser, you could bring up that ASCII table again. So go to the ASCII table, and you had it. You Googled it before.
Oh, sugar! I lost you.
Yeah.
Where are you?
I can see you, but can you see the Zoom?
There we go. I'm back.
Yeah. Okay. Yeah. So, all right. So take a look at this. It's a terrible table. No. We need one that explains what the codes do. Can you find a different one? Yeah, that might be better. Click that one. So we can. Okay. All right. So you can see that 0 is null. Then, ASCII 8 is backspace, which if you think about it, if 1 is A and 2 is B and 3 is C, D, E, F, G, H, right? So 8 is H because it's the 8th character in the alphabet. And you can see that 13 is carriage return, right? And that's the equivalent of Control M, because M is the 13th letter in the alphabet. And if you did, and you can also see that line feed is 10th. So that's so number 10 is line feed, and that would be the equivalent of, well, if Control H is backspace, IJ, it's Control J is line feed in ASCII. And so that's all is happening, is that we are doing a control key, and then an ASCII number comes in from the terminal, and we trigger a piece of Mint code. So I was just about to show you the Mint stuff. So go back to a Z80 now, and you can see we've got all these different commands. Now, there's nothing about ASCII here. All we're saying is this is the backspace routine. We're going to wire this into a table later. But basically, this is our backspace routine. The next, and then re-edit. We have edit and re-edit. Those are 2 commands that, and you probably don't know about re-edit. I think you found it by accident. It was like Control J or Control L. I can't remember what re-edit is, but anyway.
Control J.
Control J. Yeah. So that one is what it's called re-edit, which is to re-edit the one you've just edited. Edit, on the other hand, asks you which one you want to edit. So it uses a question mark to do that. And we can go into how these work in Mint and maybe in a bit later, but you can see that the first one does a backspace, and what it's doing, backspace is basically removing one character from the input buffer, and it's also...
Is that part there, is it?
No, look, go to line 49, line 50. This is doing backspace, and that's moving the buffer. It's actually using the /C variable, which is the tib pointer, and it's subtracting something from the tib pointer. Does that make sense? So the tib pointer is what you've typed in. So you type hello, the tib pointer points to the last thing you type. So HELLO. When you do backspace, what it does is it reduces the tib pointer by 1, and also it prints. It also wipes. It also wipes what has been typed there before. So I don't really want to confuse you about this, but that /C, that //C should be seen as that's the tib pointer. That's the current character, and we're trying to reduce it, right? So, yeah, and so, yeah, that's basically what's going on there.
Why do you shove it in?
Yeah, we grab the tib pointer, and then we subtract 1 from it, and then we write it back to the tib pointer.
So what was with the @ symbol here?
That's to get the value of the tib pointer and put it on the stack, right? The tib pointer is just an address, right? /C is just an address.
Hang on,
this is called fetch. The @ character is called fetch. It's a command which says, give me an address, and I'll give you the value that it's pointing at.
Sorry, I just had an interruption behind me. I was up to here, the @ symbol, and then the.
Okay, so think about it this way: /C, when you do that in Mint, it returns the address of the tib pointer.
Gotcha.
But it doesn't give you the tib pointer as value. It gives you the address of the tib pointer.
Okay. Yeah.
You then need to do fetch to get the value of the tib pointer. Then we push 1 on the stack.
The fetch is an @. That's the fetch, the value.
Yep.
I'll write this up just quickly. Sorry.
Yeah. So, I mean, you've done plenty of stuff with variables before, right?
Yep, getting there.
Yeah. Well, you know, you have to
reduce.
Yeah. By 1, and then store it. So store. Yeah.
There's our exclamation mark.
Yeah, there's the exclamation mark.
And then you've got a comment here. What's this bit?
No, it's actually printing. It's actually printing on the terminal. It actually prints a backspace character. It actually moves the cursor back 1 step with the /B. So this is a string that is understood by the terminal. It's saying it's doing a backspace. It's then printing a space, and then it's doing a backspace. And that is the way to erase a character on a terminal.
So why is it doing it again here? Sorry.
Well, if it didn't, all we would do is we would reduce the size of the tib internal memory buffer, but that wouldn't be telling the terminal what to show. So
up to here, it says to the terminal, go back 1.
Yeah, so it moves the cursor back 1. It then prints a space character over, so it overwrites the thing that has just been backspaced over, and then it does another backspace.
Oh, I'm just a little bit confused.
Yeah. I mean,
do you see what I highlight when I highlight like that?
Yeah.
Okay, so this first one here, sorry, it actually starts from here.
So if you started Mint, you'd see what we were doing. But basically, what happens is you hit Control-H, and it will
backspace,
and it will move the cursor back left 1 character. It will then print over the top of the character that you've just backspaced over. Because if it didn't do that, the cursor would move, but the text would still be there.
If I do it now, like in this editor, there's command and hit backspace, it actually gets rid of the character, doesn't it?
Exactly. That's right. Well, imagine how that works. So what you just did then is, this is it exactly.
That's arrow, left arrow.
Yeah, well, that's what backspace does, is it just moves the cursor. It doesn't actually
I thought
do anything.
Backspace was to delete as well. It's not.
Yeah, no, it's not. So, I mean, that's what we wanted to do. But yeah, it moves the cursor left, and then by printing space, it overrides the D, like where you
How did we write space? You mean /B is a space as well?
No. /B is a move left, so it's a backspace. So the space is the space between. The space is the space between the two /Bs. So select the in that, yeah, that is a space.
For who?
Okay, because it's inside this back-ticked string, right? The
Ah,
string
it's part of
says
the string. So the
print
space
this.
is actually in this as well, right?
Yeah, okay. It's a little confusing because we're working at so many levels, right? So it's just one of those things that, and you want to put some semicolons in front of those if you're going to keep these as comments.
Yes, yes.
So,
The space between the /Bs is what? What do I write here?
Yeah. So you'll realize that when you try and do kind of terminal operations yourself, is that this is kind of like a sort of a formula for doing a backspace. Is to move left, then to override with a space, and then move left again. It's just a way to do to control the terminal. But the other part with the /C is all about controlling the tib pointer, which is not visible, you know. So let's not worry about it. That's just to give you an example of a control key mint macro. And you can see that we have a re-edit macro, we have an edit macro, and I'm using the word macro to mean control key type thing.
I was just going to ask that this is for like a VT100 terminal standard.
Yep. Right. Absolutely, which is controlled completely by ASCII. Okay.
Yeah.
We could even change the color of the text. You know, there are ways of doing everything with a VT with an ANSI compatible terminal. There's a whole bunch of stuff that Mint could do. Just even
you could play a character game like this. You could have like a moving sprite.
Yeah, exactly.
This is good. Dungeons and Dragons, here we come.
Well, given that a Z80 is a bit brain dead in every other aspect, it is a full implementation of a terminal. And I haven't done a lot with it, but you can change text and you can make the cursor move up, down, left, right. You can do all kinds of things. So nice. I just haven't explored it that much. But,
later, when things got nothing to do, rainy day.
Yeah. So now getting on to re-edit and edit, you can see that basically these are using /6 and /5. Those are special routines. You've already come across them. Basically, I pushed these kind of specialized routines that I needed to call from Mint into these numbered routines because they're not used very commonly in your normal programs. So we see /#number. That is a special command. And you already asked me about these commands before.
What line number are you talking about?
59.
Oh, I was ahead of you.
And 62 and all of them. Every time you see /#number, see /6, see the #6? Yeah, that, right? That is a numbered low-level routine that isn't really easy to use from Mint, but it's kind of like very low level, so you're not likely to need them very often.
What is 6 anyway?
You could find it. Command 6.
Edit command value was
there. We go. Yeah, was it exactly. So that's the guts of the edit routine, right? And you're looking currently at the re-edit routine, but you can see it's being used in line 62 as well, right?
First time I used this edit, my expectation was to go back on the line, not actually lose the characters, but actually you have to delete everything as you go back.
Mm. Oh, well.
Classic word processing,
sure.
You don't actually lose the characters till you're
You've
ready.
just been too spoiled by 40 years of everything being served up to you on a silver platter. No, the point is it's actually quite hard to... Yeah. Well, not so much. It's just it's quite a lot of work to make a proper editor. And
Control L, you've got a mirror copy above you. If you can't remember, you just retype it from there.
Yeah, and if you think back to those early Commodore 64s and earlier Sinclairs, they didn't give you a whole lot of help either. Oh, they did actually have a decent editor. But what I'm saying is that the line editor is a bit of work, and I haven't had time or space to do a decent line editor which would control the characters, so you could then go in and then hit delete. Yeah.
Well, the whole idea is to have short command lines anyway, not to have long ones.
Well, that would be a classic Charles Moore thing to say, is you don't need it anyway, and just deal with it. But even he wrote editors and stuff, so it's more about a job for the future. not now.
Sure. I
And
mean,
so,
you could edit offline, then upload. You could use your own favorite editor. You wouldn't even need me to do the editing for you.
yeah.
Okay, so that's the last
Oh,
thing.
yeah. I mean, that's right. You can do all. Yeah, that's right. It says only when you're wanting to talk directly to the tech one. Its editor is very basic,
Yeah.
very, very simple. So we've got re-edit, which
Huh?
is the last defined command.
Which line? Sorry.
Okay, well, re-edit
Oh,
58
re-edit. Yeah.
remembers the last defined, the last thing you edited or the last thing you entered. It remembers it, and then it brings it back into for you to edit. What that means is it copies the content of that command definition into the tib and prints it on the screen and invites you to edit it and then re-enter it. So it gives you the ability to go back and
That's good.
fix it.
Because you tend to re-edit the last thing that you edited because it didn't work after you changed it.
That's right, exactly. And when it's a bit like the history command you were kind of wanting before. Well, I haven't stored. I only stored the last thing you edited in a single variable.
But Control L shows everything, which is quite good.
Yeah, everything you've defined, because we know what they're called, because they're always got to be an alphabet. So therefore, it just goes through the alphabet, looking at A, B, C, D. If it's empty or if it doesn't have anything in it, then it skips it. Otherwise, if it's got some length, then it will print it. And that's what list is doing. So on line 64, that's the code to do that actually prints the prints the whole program in written in MIN.
Complicated.
It's a little complicated, but you can see there are only 26 characters that it needs to go through. That's what 26 represents. So it's actually the /I is going 0, 1, 2, 3, 4, 5, 6, 7, up to 25. So from 0 to 25 is being looped. That's the value of the control variable /I at or fetch, right? Then what we do is we add 65 to it. So in the case of 0, it adds 65. Well, 65 is the ASCII for the letter A. And so it's gonna then see whether or not A has any content. I'm not going to go into too much detail because I can't remember everything myself, but it basically checks to see whether there's any length to that definition. So maybe you didn't define
this
anything.
Part here.
Yeah, there's some code there.
That checks this part here.
Yeah. Okay. It basically gets the definition and you see it uses /#6. #6 gets the definition and writes it into the tib. Okay, it gets the definition, and normally you would use it to print it. Well, let's go back. So it just gets the definition, and what we do is we work out whether it's 0 in length. If it's not 0 in length, then it's a definition that we want to print.
So anything greater than 0.
Yeah, that's right. Otherwise, it would print A to Z, but most of it would be empty, which I didn't think was very useful. But, it only prints the commands that you've defined, in other words.
And this part here says send it to the line, to the command line.
That's a carriage return. Yeah. And then it prints the definition that's in the tib. So
#5.
Yeah. #5 is probably a command you might not have any detail on, but yes, there it is. Just go back a little bit. There it is. Print. Oh, it prints a prompt. Yeah, so I was actually incorrect about that. It prints, so #6 prints the thing, but the only if it's greater than 0 will it do a carriage return followed by a prompt. So you can watch how it behaves, but if it's empty, it won't do a carriage return and it won't do a prompt. So if it stays
as it was.
Yeah, it stays where it was. So that's the way I achieve that result of only printing the visible or the worth printing ones. Yeah. Print stack, that's your other favorite command, and that's controlled by Control P, and use it to see the state of the stack. And it also prints a prompt at the end with the #5. Toggle base, that one's a very easy one to understand. You would have been able to write this one already based on what you know about Mint already. But it's going, get me the base value. So it's /b fetch. Then it compares it with 0. If it is equal to 0, sorry, it checks to see whether it's equal to 0. And if it is, it will return 1. But if it isn't, it will return 0. So what it does is it flips the value. It inverts the value. So if the stack has got a 0, and it will go 0 equals, and it will return true, the stack will now be 1 if it was 0. If it was 1, and it did 0 equals, it would return false.
No, it's a bitwise invert. Okay.
Yeah, I wouldn't call it bitwise. I call it logical invert. Did I say bitwise? I probably did. But yeah, it should be just it inverts the Boolean value. Okay, not it doesn't do bitwise flipping. So if I've got the word bitwise in my documentation, we better remove it.
I might have just made that up.
Yeah. So it's an invert. You're correct. It's a Boolean.
Invert, yeah.
Yeah, and so 0 equals is a very convenient way to invert a Boolean.
Yep.
And then we store it back in the base. So because the base is just simply a Boolean flag, which is either true or false. If it's false, it's decimal. If it's true, it's hex.
Base.
Yeah. So it basically says whether or not it's base 16 or not.
Gotcha. Yeah, that was simple.
Otherwise, it's decimal. Otherwise, it's decimal. Fourth is more sophisticated. It has a base variable, which can be, you can literally work in base 3 or by base 7 if you wanted to. You have to be pretty crazy to work in any base other than binary, hex, and decimal. But you might like octal, for example. You can do that in fourth because you can actually set the base to be any number up to 26 or up to 36 base.
Playing with bases, would that be a trick to do logarithm down the track?
Changing the base?
Yes.
Yeah.
I seem to recall some maths that where you divide two different bases, you can actually derive the log of the number somehow.
Yeah. Bases are all connected to logs for sure because, and yes, if you can work in bases, but I don't know whether the fact that you change the number base will be much use in that case, but maybe it is. I'm not completely sure.
Overcomplicates it.
but I mean, fourth is overcomplicated in this area. In other words, it's a perfect solution, and sometimes I wonder whether it was the best idea. So that's why I've only got hex and decimal. I didn't think it was.
And you got base 10 as well, anyway.
Yeah, decimal is base 10.
Decimal, yes.
Yeah. Okay. So now let's go to the start of the variables. This is a table that we use to copy. So these are values that get copied into a table. So you know those /A/B/C/D/D/E, their initial values are stored in this table. So these get copied into RAM at startup. So you haven't seen the initialization yet, but this data is going to get copied into the variables as part of the initialization. Yep. Okay, so you can see that, for example, S0 is the start of the stack. And so its initial value is D stack, which is the start of the stack in memory. If the address D stack is going to get copied into S0, which is, sorry, that's a confusing name, but /A, the variable /A, is going to get initialized to the value D stack, because that's what this variable that's inherited from, that's the name of it. It means the start of the stack. I copied it from fourth, so it's probably a bit confusing. So /A
means absolutely nothing to me. It's like weird.
Yeah,
that's sort of that's intuitive too. Intuitive.
Well, let's expand it and just call that start of data stack. It's a constant. It doesn't change throughout the course of the program. So start of data stack, and you can see that we initialize the base to false, which means decimal. Oops. Oh, now we've got lost. Okay, back. Here we go. Stop. Okay, so the base is false because the base 16 flag is false. That means we don't have base 16. It means we have base 10. So we're doing decimal, okay?
Yeah.
Okay, moving on. The start of the tib pointer is pointed to the start of the tib. So we set it to 0. 0 is the offset into the tib. So we add the start of the tib to the tib pointer to work out what the address of the character is. So 0 is the start of the tib in this case. It's an offset, if that makes sense. So yeah, it's an offset into the tib. Yeah, okay. D doesn't look like it has any purpose. I can't remember what D is. The last def is it just says the last definition that you defined is set to A. So if you do a re-edit, it will re-edit A. So it remembers the last command that you defined. So if you define :C blah blah blah, then this variable will be changed to C. Does that make sense?
Sort of. Yep.
Okay, so F, I can't remember what F is. This is all to do with namespace stuff. You can ignore those, I think. And then the last one is that the heap pointer /H is defined to be the start of the heap, which is the last defined memory. So that's the start of the free memory, which can then grow to fill all the available RAM that you've got with data and program.
What's this one here? Page 6.
It's something to do with, it's something to do, page 6 is we have pages. I'm not sure why I've put that there.
I noticed something that says do not cross a page.
Yeah. We'll talk about pages and then we'll come back and I'll probably remember.
That's to do with like jumping and branching in assembly. Don't go too far. You'll exhaust the 256 range.
Exactly. So you know what a page is in this context. It's 256 bytes. So the whole of Mint is broken up into various pages. And page 6 is, I think, the last page. We'll get to the pages shortly. Okay, here's a table. Now this, you can see this lit.dat and rep.dat. These are the macros that were used for compression purposes, okay? So it's telling you that the next 4 items need to go into the table, okay? So it's basically saying, so imagine this is a table of bytes. And what we want to do is we want to get the least significant byte, LSB, of the exit routine. So, you know, exit is a label, so it's an address in the ROM somewhere. It'll have an upper byte, which is called the page byte, and it'll have a lower byte, which is like an offset into that page. Does that make sense? An address is basically 2 bytes. So we only want the lower byte. We don't care about the upper byte because
in brackets means the address of this label. You know what I'm doing? Double clicking.
Oh yeah, okay. Oh, is that what you're doing? That's because we've got to talk to Martin about fixing this. This double click, you've got to stop double clicking now because I have had to reprogram my entire brain to deal with the double click in Z80. It's useless. It's completely useless. Sorry, Martin, if you're watching this. And
I was just trying to highlight something. That's all.
Yeah. So don't ever use double click.
Okay.
All right. So that's what it was.
The address of exit is going to be LSB.
Well, no. LSB says give me the least significant byte of the exit address.
Right.
So if you looked for exit in the further down, which we can do. So you could do a Command F, Control F, whatever you need to do on your on Windows. You should be able to bring up the search engine. Yeah. Now type exit underscore into the search. There it is, right? So that's the label. But the point about the the table is it doesn't store addresses, it stores offsets into pages. And this is actually a scheme that Ken came up with, and it's very clever because it means that we can have a table of only bytes, not addresses. Because an address is 16 bits, it's 2 bytes, and it's quite slow to load. But if you already know the most significant byte already, then you can quickly jump to a routine by just getting the least significant byte and putting it together into a pointer and then jumping to that pointer. Okay, so exit, let's do this. See in the tech1 rom 10 z80.list file. Yeah. Now go to exit here and search here using search for exit again. Okay, here you go. You can see that EB, this is the address of exit. It's 01 EB, right? So we only store the EB part. We don't store the 01 because the 01 is the same.
Redundant. Yeah.
It's redundant, exactly. So we group together commands into pages. This is purely an efficiency thing. You can implement this. You can implement this a lot more in a more readable way, but it would be much slower. So LSB, in fact, sorry, search again for exit. Sorry, that's not what I want to show you. Search for the, yeah. It's actually at 0, go back. No, search, use the search. Oh no. You've lost the underscore. I don't know why the underscore is gone.
Oh, I thought you told me to remove it.
No, now search again. Click, see the left and right arrows, that one? Yeah, click on that. Okay, this is the exit routine. What I'm trying to say is exit is actually 0463. Okay, the address it assembled at is at 0463. Are you seeing that?
Yes, this is the real code. This is what the macro created.
Yeah, so what I'm getting at is the 0463. Do you see that?
Yes.
That the 63 gets stored in the table, not the 04.
Oh.
Okay, the 04 is
in page 4, right?
Exactly. So that's what I'm trying to get at, is that when you look at that byte array, it's going to have 63 in it. So if you scroll back to the exit, the first one, you can see the 63 is the actual value, right? And that's because that's the least significant byte of the exit routine. We know what the most significant byte is 4, but the least significant is 3. So anyway, that's just to give you an idea of what the table is doing.
Assembler was so powerful. This was crazy.
You can do some cool stuff with assembler. It's one of the most fun things about. I learned a lot of this from studying Forth. There's no question that this stuff came from Forth. So so what I'm showing you is a bunch of routines stored into a table. Now you could go back to the source file again. That one. Yep. The first one. Yeah. Oh, is that the one? Oh, sorry. I meant mint asem. Sorry. Go back to mint asem. Yep. Okay. Here we go again. All right. So we could scroll. If you could search back to the table again. So use the left arrow in the search. That should get you there. And again. There we go. All right. So what we're doing is we're saying the next 4. So lit dat 4 is saying the next 4 things are literal data. You don't need to think too much about this, but let's scroll down to line 99 and just say that, so what's happened here is we're now starting to lay the commands down. So we've got at the ASCII table for exclamation mark, I'm storing the least significant byte of the address to the store routine. Okay, so the store routine is being stored at the place where the exclamation mark is. And if you remember mint, what exclamation mark means, it means store, right? So the store routine is being associated with the exclamation mark. Okay, does that make sense?
Yeah.
And the dupe routine is being associated with the double quote. You should be able to recognize that, and swap is being associated with the $sign, and the over is
What's this
okay. that's logical and. So it's
I've
and
never
I
typed
suppose
that.
and or. You haven't done anding operations. Yes, you have. No,
Oh.
you've done or. You've done or. Yeah, you haven't done.
Logical and I haven't used it. Okay, it's
Yeah,
there.
it's not bitwise. Is it bitwise? I can't remember whether it's bitwise. I have a feeling it's logical. Anyway,
That's
so
across all 16 bits.
yeah, maybe it is right.
It's 2 words. It's a word.
No,
Right.
it is a bitwise and yeah, and that's fine. That's good. All right.
It's like
So
or the masking effect of or
yeah, that's
using
right.
these numbers. Yep.
Yeah, so all this stuff that you normally do in assembly, you can do using and
Beautiful.
or. So what else have we got? Swap.
Begin. These are all familiar. Yep.
Yeah, the only one that's a bit quirky is hex at line 101. And what that's doing is it's saying that when you see a hash, then the characters behind it are going to be, the characters follow it are hexadecimal.
Yeah.
And so it triggers a hexadecimal parsing routine at that particular point.
And then it defaults back to decimal because that's standard input.
Yeah, that's right. So
your divide is freaky because you get 16-bit and 8-bit combined together, and you got this leftover stuff and like what?
Yeah. It's a bit. It's really cool. It should be called /mod, but you know. So in fourth, it's called /mod, and they have They have so many different divides and multiplies. You know, they're signed and unsigned and all that stuff. What I've got is very primitive. But yeah, so it unfortunately has 2 results, which is a little confusing.
That's the fun of it.
Yeah. So we need to.
I'll update that here.
Yeah, there it is.
Where are you?
Yeah, it looks like it's. Yeah, it doesn't show the. It's
the wrong way.
It's not
showing
showing
that way.
No, it's not the wrong way.
Is it this way?
Yeah. So, but it's wrong because it should show the remainder. So it should have the quotient and the remainder. Okay, so it should have 2 results. Yeah, C and D. Okay, where there's space between C and D, right? All right. So C is the quotient. That's what happens when you divide a number by another number. You get a quotient. And D is the remainder or the modulus, depending on your preferred. C is the quotient. That's the actual whole number. The whole number division. What do you call that?
Quotient. How do you spell it?
Quote IANT. Yeah, that's correct. It's ENT. I'm pretty sure that's correct. Yeah. And D is the modulus or remainder. Remainder is perfectly fine too. Okay, and you usually have to throw away one of those things, because you're usually only after one or the other. But that's just the way division is. You get both because sometimes it's useful because you can look at it also as the numerator and the denominator. You're actually looking at the. No, I won't confuse you. But the main thing is you can, if you've got those 2 values, you've effectively got a fraction. You've got the whole number.
Which is pretty accurate, yeah.
Yeah, exactly. Yeah, that's right.
You can repeat the cycle and keep going. And
exactly. So it doesn't work in floating point numbers. It uses fraction. Works in fractions mainly, which I think is pretty good for accuracy. But anyway, especially because we're working in 16 bits. But sometimes you're gonna need more powerful stuff than what we've got here.
Well, the telescope job will require it.
Absolutely. Yeah. There's some articles that you'll be reading on.
You move a telescope 1 degree, that's a lot of space in outer space.
Yeah. And you're going to need more accurate than 16-bit. You're going to be probably needing 32-bit. Yeah. Anyway, so hex, swap, over, and drop, begin and end. A begin and again are looping functions, right? So line 106.
Yeah.
That's the start of a loop.
Yeah.
And it obviously needs a number before or something on the stack before it executes. Yeah. And then the begin and again are classic names used from fourth. So loops start with the begin and they end with it again. They start with a begin followed by again. That's just the way fourth calls loops.
This is even more elegant. It's just one symbol, bang,
Yeah,
and you
I
know what it
agree.
is.
The problem with fourth is there's too many different types of loops, and they've got do loops, begin loops, etc. We've got multiply, we've got add, we've got h dot, which is similar to dot. So if you look down at dot, full stop,
Hexadecimal dot, yeah.
yeah, so you know hexadecimal dot. That's what
Yeah.
h dot stands for. Sub is just subtract. Dot is just print the number on the stack.
You know, the
And-
H dot is a quick way to mentally work out the binary as well, which is good.
Yes, yes, yes. It helps. I mean, hex is very good for that. So, okay, now if you get to line 115, you probably wonder what the heck this is. And what it's saying is we're going to repeat the lowest significant byte of the num routine 10 times. Okay, so it's repeating num routine 10 times.
Repeat.
So repeat the lowest significant byte of the address to the num routine 10 times. And you can say repeat 10 times the least, it's up to you. So what it's doing is you need to find the num routine, and it's going to take that least significant byte and just keep using it again and again and again and again. Okay, there's the num routine. Actually, it does a jump to another routine called num, so you need to go to that. You can do num colon. It should get you there. Num colon. Put a colon in the search. Yeah, there you go. And that routine is used for reading the numbers and understanding the numbers. So if you go back to the tape.
What's it doing there? 0. And
yeah.
then
It's
that's a register address contained in the register in A.
I'll tell you what it is. BC points to the input from the interpreter. So it's like the instruction pointer. It's telling you where you're up to. So BC is the pointer into the RAM, which is where you are in the program.
So you've already pre-allocated the general use of each register for functions within.
Yes, but I've reserved a few. So BC is one.
You reuse them for that, right? Gotcha.
Yeah, yeah. So BC is kind of left alone. We don't use it in general use. I'm careful to never damage BC, but all the other ones are free to use for other purposes.
If you do, then you just push it on the stack, and then.
That's right. That's right. You have to do some tricks, which we'd have to.
I've always got this lingering thing. If I can't fix it in Mint, I can back out to assembly and then come back in, but I don't quite know yet how to do that.
You can do it though, and that's the idea. But you've still got to be careful with BC. Okay, so you've got to, if you start pushing it on the stack, you've got to start working out how the stack interacts with what you're doing because of the funny way we use the stack. Okay, so if we just go, okay, so we're going down, yeah, good. See that num thing, line, stop 115. It's just basically saying at the ASCII value, which is 330 hex, we're going to use a num. And then at 31 hex, we're going to use num. And 32 hex.
Sorry, what's 31 hex? Where are you getting that from?
You can't see it because we're up to 31. We're up to 30 in the ASCII table. So, okay, scroll back a bit. So you can see that we've done 30 characters already. If you go to the very start of the table, it's, okay, opcodes, right? I opcodes. It's 4 literal bits of data, followed by 29 NOPs, followed by 15 data, and those are, so lit data means
you're adding that plus that plus that.
Yeah, exactly. We eventually get up to 30H, which is the hexadecimal for the numbers 0 to 9. This is
our compressed skip thing. Fast.
Yeah, exactly. So now we're talking about mapping 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 to the routine num, and then leaving the num routine to interpret what the number actually means. So in other words, all the number letters 0, 1, 2, 3, 4, 5 all point to the same subroutine, which is called num. Okay, because they're numbers, and that's the way it works. The next, and then after the numbers, we have the characters colon, semicolon, less than, equals, greater than, question mark, fetch. Okay. And you can see they're being mapped to the least significant addresses of routines. Colon is going to def for defining a command. Semicolon is saying return from command. Less than is going to the LT, less than routine. The equals goes to the equals routine. The greater than goes to the GT routine, greater than. And the question mark goes to the key input routine. So you know that already, right?
Weird name.
It's actually, that's again a bit of a fourth thing, but that's what question mark does, is get the next key from the keyboard.
Okay.
And then the next characters are the ASCII for capital A, line 126. You can see there are 26, and they're all doing the same thing. So the ASCII for the letter A, the ASCII for the letter B, the ASCII for the letter C, the ASCII for the letter D, all go to this routine called call, okay? And what it means is if you see in your Mint program a capital letter, it's you want to call a command with that letter. So what's happening here is this is how you execute. So it's going to execute a letter command.
You do the same thing with slash capital letters as well, don't you?
Yeah, except
Or
slash
not yet.
capital letters are not defined now. They used to, yes, they used to. Yeah, but now they've kind of they're free to use for future Mint. I just wanted to get rid of them because they were a bit weird and hard to explain. So I just got rid of them.
Okay.
Okay, so the 26 letters of the uppercase letters of the alphabet have been associated with the routine call, and then we do 6 more, which is square bracket, slash, close square bracket. Okay, so that goes all the way to Z. Yeah. Okay, so now we're on line 129. You can see that the next 6 bytes are basically square bracket, slash, etc. And these are being associated with array definition. Slash is being associated with alternative command. Close square bracket is end of an array definition. The little character is exclusive OR. That comes from C, I think, that syntax. The lowercase, sorry.
Sorry to interrupt. In the C syntax, there's actually quite a large library of possibilities that may or may not be of use in Mint. Would that be right?
Could be. Well, yeah.
Like there's lots of these syntactic styles of characters and combinations of them.
Yeah. At the moment, Mint only has 1 character per command.
Yeah, you don't want to make it too complicated.
It could be expanded though. It could be expanded. Okay. And I'm starting to think that's what we should do, is that...
Because we want to be more machine orientated, closer to the metal.
Yeah. Well, you also want it to be able to be read more easily. So sometimes a command like less than and equal to is represented by a less than followed by an equals, right? Yes. That could be made to work. It's just that you need to have a slightly smarter parser, and because spaces aren't used ever, whereas in C spaces are necessary in some cases, it's a very simple parser at the moment, but it could be made slightly smarter. So
potential there. That's good.
Yeah, so underscore, definitely. I'm thinking about some of that because what I really would.
But yeah.
No, it's good, and you can see underscore is a negate because it looks a bit like a minus sign. It takes whatever values on the stack and it.
I haven't used that.
It's a good way of negating a value. So if you wanted to subtract 1 from something, you could get 1 and negate it, and then add it to your original number, and it would be the same as subtracting.
So what's the formula? How does it?
You use one negative. Like if you want to make -4, or whatever, an underscore.
1 negative equals.
Why? No, not negative. Underscore.
Yeah, underscore. Yeah.
No, 1 underscore.
And what's the result of that?
-1. on the stack.
which
But,
looks like
is
in two's
FFF,
complement form, which is actually a big number.
which is FFFF. Okay, so it'd be the equivalent of hash FFFF. Yeah, that's it. So, but when you add FFFF, it has the effect of going down.
So negation. I was wondering about negative numbers.
Yeah, we don't have.
There they are.
Negative numbers are not exactly handled natively in
No,
Mint. You basically
they're not
work
truly negative. You've got to understand what they are.
Yeah, because in machine code there aren't. I mean, we don't have, like in C programming, we have concepts of signed and unsigned language, signed and unsigned numbers. That's also true in Forth. But in machine code, we don't. We handle whether it's signed or unsigned sort of manually in our assembly language. We have to think that way, but they're basically positive numbers, and then we think about two's complement and all that stuff. So this does a two's complement on the number on the stack.
Yeah.
Okay, moving on. String, right? This one is actually for printing a string. It will take that tick and it will print everything that occurs after that tick until it finds the next tick. Okay, so it's equivalent of print. Yeah, and it handles things like carriage return and backspace and other things by using ASCII. I won't complicate things. Just say that it prints whatever's between the ticks. Ignore that carriage return stuff because I was being confusing there. I don't think we want to talk about that because we're talking about writing in Mint, not in assembly language. So this is how you print out a string, hello world, is you go back tick, hello world, close back tick. That's it in Mint. So the next, on line 136, we repeat the least significant byte of the variable routine. And you might be able to guess that the reason why it's 26 is because it's the lowercase letters A to Z that are associated with variables.
That's right.
So there you go. So that's what we're up to now. So it's A to Z lowercase will take you to the variable routine. Yep. Exactly. Then we go to the next one, which is, I reckon, a funny one, but we got it. It means shift left using a curly brace. I'm not super happy with this, but it is a useful command.
It is useful. It's how bitbang works.
Yeah, exactly. So I think most people who see Mint for the first time don't expect curly braces to do that. But anyway, that's the way it works. Or is familiar. It's just your normal or. Yeah. Tilde is a bit weird. It's the rotate routine. And you pointed out that documentation is slightly incorrect, but basically it rotates. Well, you said that it rotates the top two characters or something like that, and it's actually three.
Oh, there was a typo. Yeah, it was about the nodes, but the function's correct.
Yeah, the function is fine.
Yeah, function.
But the documentation is wrong. So we will not that one, the other tilde, wherever it is. There it is. Yeah. Rotate the top three members.
Oh, rotate top three, yep. Looks so good.
All right.
And then was the other one, which is a smaller cousin. That's swap.
That's right. Exactly.
That's sufficient, isn't it, for stack stuff?
Yeah, it is.
Swap,
it is.
Rotate.
Yeah, because we're using the machine code's return stack for the data stack. So it's pretty quick. And it works pretty well. So that's a rotate routine. It's such an important routine that I decided to give it a special symbol. The next one, 143, is not used really. So it's been associated with NOP, which means no operation. It's a different key on your machine because you've got Windows, you've got a delete and a backspace key. But honestly, I don't know whether it's useful in Mint. So that's why I haven't done anything with it.
So it does nothing at this stage.
Yeah, it does nothing at the moment.
The time waster. Okay.
Exactly. Yeah, we've already wasted time on it. That's for sure. So moving on. Moving on again. We're moving now.
Well, that's like this one. This is like 1,000. Nothing.
Exactly. So now we then with the next 17 are associated with the control keys. And this is could be interesting to you because these are the ones that link back to that table earlier. So toggle base, edit, backspace, re-edit, and you can see they're associated with the ASCII for certain things. So you may or may not know them all. Control B toggles the base. Control C does nothing. Which one was the one that was caused the crash? Was it tab?
Tab, yeah.
Control I, in other words.
Yeah.
It shouldn't do anything.
Interesting.
Okay, well, we'll get to the bottom of that later, but it says it hasn't been allocated, but it could have been destroyed somehow. Let's not worry.
Alt and Tab freak it out.
Interesting. Okay, well, it could be your keyboard too, so we just need to get to the bottom of that. But Tab is control. Yeah. Well, Control I gets you is the tab. You can see Control J gives you re-edit, and which is also line feed. Control K does nothing. Control L gives you a list, and Control
What
P
does that mean? INT doesn't do anything. Okay.
Yeah. That's what
What's that? Form feed, is it?
That's right.
And
Normally that would print out a page of paper. Carriage return.
Oh, carriage return.
And and I don't even know what DLE or
CRLF is 2 of them.
Yeah,
right, they're not 1. Okay.
So it's Control M followed by Control J. Yeah, you would see MJ come through in control sequence. Control MJ, Control M, Control J.
Well, some printers are set up with these control characters, aren't they? That way you can program.
Yeah.
Tell the printer assume this particular mode.
When I was
the following characters will be understood.
When I was studying engineering, we still were working with terminals like these, because we had to learn on punch, paper card and all kinds of ancient stuff in the early 80s. But we did get access to these very nice, VT100 type terminals. And we, as kids who'd never ever played with computers, realized that we could go Control H would get you a backspace, and then Control M would give you it would take the cursor back to the start of the line, but then you'd have to do a Control J to get it to go to the next line. And so, and all that stuff. You had to learn how to use the terminal, but that's how ASCII control sequences work. And it's still the same to this day. All right, so moving on. So that's how this table is now all of the control keys have been defined. And then if we keep going, we've got some empty stuff. I can't remember why that's empty, but I think it's because the space from P to the start of where we need to be is 15 characters. Then we get to the alternative, the slash commands now, right? So that's a space, SP.
That's a space.
Oh. Yeah. Then we've got slash exclamation mark or alternative exclamation mark, which hasn't been defined. Doesn't look like it's got a definition. You did need to look there, because if you look in the source. No, go to the source. No, go back to the assembler. You can see it's not defined. It's got knob. Right. So you saved some time. Yeah. So you can see there's no slash quote.
I thought I was dumb enough to write some notes about it.
Yeah.
Why is it here? BBA slash.
I don't know, but I don't.
You told me this the other day.
Well, maybe you're typing literally. I can't remember. We might go back and correct that but it looks like it's wrong, whatever it is. I don't think there's a slash exclamation mark for any purpose. Nothing in Mint doesn't exist yet. And we don't have enough ROM to implement it, even if we wanted to. But that's how we could add it if we needed to, is we would put it into this table.
What does slash mean in C code, perhaps?
Slash means escape
exclamation mark.
Oh, escape exclamation mark doesn't mean anything in C.
Doesn't mean anything.
Yeah.
For us, it means store it somewhere. This is maybe a different type of storage.
Yeah, it could be. In fact, why didn't I implement it? I mean,
store it on the hard drive.
No, I've got a feeling it does have a meaning, but I'm trying to understand why it's not. Like, I thought there would be a character store, like it's equivalent of C store.
Maybe,
I,
maybe in fourth. It's got a meaning in fourth, perhaps.
yeah, can you go back? I don't need this.
Sure. Sorry.
If you look for C store, like search for the command C store.
C store.
Yeah.
C, like that.
No, C, type it out. C followed by the word store. Yeah. Yeah. So where's that being pointed to? Can you, oh, it's not being pointed to by anything. I must have turned
One
it
of
off.
one.
So anyway, that slash exclamation mark does do something. It's for storing byte values, but for some reason it's been disconnected for some reason. So what I'm saying is that where you saw a NOP, it actually should be pointing to the LSB of C store. That's an actual error as far as I'm concerned, because it's how you can store bytes. So all I'm saying is you got this command called C store, but it's not being used.
Okay.
So that's
Is that like a heap? It's a heap thing.
It's no, you know what store is? Store stores 16-bit values at addresses, right?
Oh yeah, that's right. When you allocate them to a letter.
Yeah, but you want to sometimes store bytes because you sometimes need to do it. And all I'm saying is that that's a bug. Can we just note that as a bug?
Where was it?
Well, you could have a look at slash exclamation mark.
Slash exclamation mark.
Yeah. Okay. So you can note this is a bug. It should be pointing to the LSB of C store underscore. Yeah. And obviously it doesn't take any space. So it should, yeah. So it should be, yeah, that's right. It should be to, and then if you wrap that in parentheses and put the word LSB in front of it, then that would be perfect. Yeah.
Is there a colon there?
Don't need the colon. That's it. So it should be that, right? That's what it should be, and then that command would work. But
Well, then we just fix it here now.
Yeah, we can fix it now. You got spell correct. There we go. Yeah, okay, underscore. All right, that's it. That's what it should be, and there should be an equivalent for fetch as well, which is when we get to slash at, you should see it should point to C fetch, which will be further down in this ASCII table. Don't change that one. No, that's to do with, yeah. So that one is, that's slash dupe, which has no meaning, okay? So I've got no idea what that should mean at the moment. So that's fine, NOP is fine. What I'm saying is that further down you will see a fetch command, as in a slash at symbol.
Yeah.
And it's further down. We'll come to it eventually, I guess. Oh, okay, there it is. See how it's got on line 194? It's correct. So that's
yeah. Okay.
And the C stands for character, but it could have stood for byte. Okay, so it does a byte fetch and a byte store, but the byte store doesn't work. And amazingly, I hadn't noticed that until just then. So we fixed the bug, right? That is actually a bug, and it shouldn't be any problem with that fix. And you can see it hasn't used up any more memory either. So I don't know what I was doing when I did that.
Just you were tired.
Tired and tired of Mint by that point, I guess. So anyway, keep going. You can see on line 171, it says /$ means print a new line to the output. Yeah. You know that.
Yeah.
You can also see on line 170, it says /# is a utility command. Yeah, and that's usually followed by a number. It's usually followed by a number, right?
Yeah. Is that a location in memory that you run assembly from, opcodes?
It's a table of special numbered routines. So you were looking at /#6 before in the re-edit command, right? And so these are special numbered routines. So /#5 prints prompt. /#6 takes a definition and puts it into the tib and prints it out for editing.
Okay. Yeah.
You know, there's a table. We'll get to that table later. So you can see that, okay, so moving on, we would say, okay, there's going to be 3 NOPs in a row on line 173. So we can ignore that. Okay, so, and then there's even more NOPs. I probably could have compressed this even further by including these 4 NOPs. They're not defined as slash parentheses slash close parentheses. They should do nothing. If you think they crash, then that's a sign of they should be. These ones are supposed to be slash parentheses and slash.
Should that have a slash there? Like
Yeah,
that?
they should, yeah. And I'm reckoning there's something wrong that causing it to crash, but you know. And so looking at this, that you can see that slash comma is a command. And what that does is it prints a character. So if you put an ASCII character on the stack and you do slash comma, it will print the ASCII. So if you put 65 on the stack and do slash comma, it will print a letter capital A.
Right.
Okay.
That's good. That's useful.
Yeah, it's very useful for sure. So you need that one. And print string is similar in the sense that you point it to an address where a string is located. So I'm talking now about 182, line 182.
Yeah, 182, yep.
Yeah, which is to print a string. So if you've got the address of a string and you put and you've got the address in the stack, and then you do slash dot, then it will print that string.
How do you know when you've reached the end of the string though?
Because the string is terminated by a null character.
Oh.
And so this is basically a C string. It's a null terminated string.
I don't know what a null is. Is that 2 zeros?
It's just a 0.
Oh,
Yeah,
just a zero.
Just a byte. Yes, a null is an ASCII control character as well, but it's used by C strings to represent the end of the string. And so then we can move on. You can see there's a lot of NOPs in this part of the table. If you then go down,
well, that one there.
it's all nonsense. Okay, so then the next one is an experimental one, 188. It's an anonymous definition. I don't think we need to.
Missing?
Yeah, it's an interesting one. Yeah, it needs a slash. All of these need slash. So I would say that's an experimental feature 188. So let's not worry about it. Instead, we could go to one that you know about already, which is 190.
Non-definition.
Yeah, anonymous definition.
Oh, anonymous.
Yeah,
and there's no definition for it.
Yeah, what it means is it will return a pointer to the routine rather than defining a variable.
But there's no code for it yet, is there? No.
It is. It does actually work. But let's not go into it because I don't think I documented it yet.
Can I just write again what it is? It's the return.
Yeah.
Return what?
Return the address of a definition, of an anonymous definition.
Okay.
So to use it, if you really wanted to use it, is you would go /:, but you then would not have a letter. You would just start putting code in and then end it with a semicolon. And instead of it going into a letter like the letter A or B or whatever, it would just return an address, which you could then
some numbers and then
and then semicolon. Yeah, you don't need to use a slash. In fact, just a normal semicolon will do it.
And what are these numbers here?
Oh, we'll just change it to 1, 2, 3 because we can't handle numbers so big as that. Yeah. Okay. So that routine, when it will return the address of this definition, and if you can call the address using the command to execute at an address, which is something like /#0 or 1, I can't quite remember what it is, then you can execute that address. And so it's like you can pass around a piece of code as a pointer. Anyway, I don't think we need to go into it because it's kind of more advanced and experimental, but that's what it's for anyway. It's an anonymous function or an anonymous command. It knows it doesn't have a letter. That's the only point about it. But going on to line 190, you can see we have input from a port. And we can see 192, we have output from a port.
These are super important.
Yeah. And then 194 is what I got you to look at before, which is to fetch from an address a byte. So this is the way you access a byte at a particular location as you use. Yes, it's a byte fetch or a character fetch. Yeah. Okay.
I've ordered some rotary encoders for this telescope stuff, which is going to output a lot of zeros and ones. These commands here, they wouldn't be able to keep up with repeating input, would they? They would need some sort of buffer in front of it to slow it down for these commands to keep reading a port, would it?
Well, they can go pretty fast.
Right.
But I don't know how fast is fast for you, so it's a good question.
Yeah. I mean, I wouldn't want to yank the telescope and then output like 1 mega pulses. It's just ridiculous.
Yeah, but the problem is, even if it is doing that, you would fill the buffer if you can't process it fast enough. You know, so right. I mean, unless you sort of compress it on the fly, you know, like if you had a little interrupt-driven routine which read into a buffer.
Yep.
And if it's a lot of zeros, it doesn't bother to keep storing zeros. It just stops reading until it changes to a non-zero or something like that. Anyway, the point is, yeah, you could drive it into using an interrupt, and the interrupt routine simply reads from the port and writes to a buffer. Very similar to this TIB kind of model. You could do that, and you could compress it. So if it's all the same data, you could just say only store it if it's changed in some way. But you know, and yeah, let's just talk about that once you've got a clearer idea of what you're doing there.
I'll do sort of a rough flow chart with some hardware, and yeah, we can talk about it.
Yeah.
I'm not even clear myself what's going to happen, but it's a differential signal, 2 pulses.
Okay.
And then if they're doing nothing, then the exclusive OR is nothing. But if they are different, then that means something's turning, which means now you can calculate the angle and whatever.
Yeah. Okay. Well, this is. I reckon Mint would be able to handle it.
Awesome.
Well, I reckon anyway. So we'll soon find out.
Just up the clock speed, simple.
Exactly. Yeah, you can get pretty fast Z80s. But otherwise, you can write the servicing routines and machine code and call them from Mint. That's the other way of looking at it.
Oh yeah.
And don't forget, Forth started as the astronomers' programming language.
You did too.
Yeah. It started in the radio astronomy, the radio telescopes
or something.
And when the astronomers saw Forth for the first time, they just blew their mind, because we're talking about like 1970, 1971.
Wow. Yeah.
When everything was really hard. You know, everything
simple
was
code to move tons of metal. Lovely.
Yeah. Every single piece of software cost a fortune, and Forth was cheap, and the astronomers could program it. So it was really good. So anyway, okay, so 198, 199, we're getting to slash square bracket, which doesn't have any meaning. Yes, it does. It's for character arrays, of course.
Is the slash in front of here as well?
Gives you a character array or a byte array. Okay.
That should be double.
That should be double. This one's meaningless, and that one go. Okay, interesting, go. So what I was saying before is, if you have an address, if you have an address, and it will execute that.
Right.
Anyway, if you pushed an address which was pointing to a Mint routine, and then you did slash caret, it would execute. Okay, so I'm not completely sure whether that's been deprecated in favor of a slash hash number, but anyway, that's another way of doing it. 203, you had a question. It's called a conditional early return, and it's for returning from a command. It's basically like a break. No, it's more than break. It's like a complete return. Like stop everything, whatever you're doing. It doesn't matter if you're nested in the middle of a function, in the middle of a nested loop or an if statement or anything. Just go, just leave immediately. So it's very intelligent return compared with the other return, which is a semicolon, which always happens at the end. This one is for breaking outside of a function. I don't know whether there's any real use for this, but I had a use, so that's why I implemented it.
Can I take you back to this one, the caret / caret?
Yep.
So this is execute mint at a hex location. So you put in a hex number.
Not a hex location, like, but an address. Yeah. So in fact,
machine address.
Yeah. So if you the stack diagram is incorrect on line 202, can you put an A before the 2 dashes? Yeah, and you can get rid of that question, and you can get rid of the question mark, because what it's saying is we don't know what the stack's going to be, but I don't think it matters. What that means is
what does this mean?
A is an address, let's say.
Yeah.
It could be anything, but A in this case represents an address. You then do /caret, and it will execute that address. If that address happens to be pointing to a string of mint code, it will execute it.
Okay.
Okay. And that's why
there is mint.
Yeah, well, we're going to get to mint eventually. Obviously, so we've been going through all the commands before we even saw what they do. But okay, so string def is equivalent of, this is how you define a string in Mint. So you know how the backtick will print? It does this for historical reasons. I think defining a string is more important than printing it. But anyway, the point is that you do /backtick, and it will actually start defining a string, and it will return the pointer to that string, which you can then use /dot to print, which was defined earlier. Exactly. Yeah. And how does it know how long it is? It's a null terminated string.
Oh, cool.
Okay, so then we've got some alternative variables. So the alt var is pointing at /a/b. So 206, looking at line 206, it does alt var, it's a/a/b/c/d. You've used them, okay? So that's what the alt vars are for. Yeah. All the way to Z. Okay, now,
so don't use the reserve ones. That's about the only thing I come across.
Yes, they're obviously exposed, but they're part of the machine, so you have to be careful. So don't use the ones up to H unless you know what you're doing. But anyway, now, interestingly enough, you asked me the question, why did I get rid of /j? And in fact, I didn't in this version. So it's still there. So /j does exist. You know how I told you that /j is basically /i plus 6. And you'll see when we get to the definition that /j is just literally /i plus 6. Yep. Okay, and that gives you the outer loop. So /i gives you your current loop, and /j gives you the index of the loop just outside. It's exactly the same in fourth. So then after that, we've got, actually I made a mistake when I said alt var, no. In other words, also those ones on line 206 are actually uppercase A to Z, and they don't do anything at the moment. I don't understand quite what's going on here.
No, you lose significant.
Oh, no. Oh, yeah. We haven't finished the table yet. Oh, sorry. Go back. Sorry. Yeah. Yeah, we got I and J, and then after that we have 16 more characters. And so we've gone from A to just before I, then we've done I and J, and then we've done...
They don't belong here. They should be somewhere else.
/A, what's the letter just before I? H. So what we're saying is we're going from A to H here. So yeah, not to Z, we're only going to H. Then so if you can just put H, so it's ... to /H. Okay. Then we got I, then we got J, and then the next line 212 is going K to Z. Does that make sense? Okay.
Yes. Yep.
Okay, moving on. So then you see that we've got slash curly brace left, and we've got slash curly brace right. And what they do is that they actually pop. These are very low level, and you're never going to use them. And then slash delete is even less, not going to get used either. So that one we can ignore. But this is just needed to pop the value from the return stack back onto the data stack. So it's mainly for popping return addresses, which is a very advanced kind of thing that you don't normally need to do very often. Is to take a look at
mint stack or machine.
Yeah, the mint's return stack. And you don't really need to work with this very often, but it's an advanced feature. But it is cool that you can do it, and I can show you applications of that later. But it's a little bit too advanced for even me to think about. You know, you've got to really get deep into it before you need to use the return stack.
Okay.
And so just moving on, let's just scroll. See
What's this one here, Del? Nothing.
Yeah, delete. It's the slash delete, which I can't see any value in that at all. Okay.
As in delete key on the keyboard?
Yeah, it's like the delete key on the keyboard, but you'd go slash and then hit the delete key, and it's not really something you can enter into a Mint program, so it doesn't really make sense.
Oh, true. No, you can't use it.
It's kind of like a control key, but somehow it wound up really late in the ASCII table, because it makes me think it was invented many years later. And so it got just chucked into a weird spot in the ASCII table. So you can see here how start is on line 231. Oh, by the way, we're just about to start now. So how long did it take us to get here? So we have
covered the lot. I'm pretty spent already.
Yeah, well, we're up to, we've got a fair way up, and this is the start of the program. So what we're doing now is we're going to print Mint 1.1 on the terminal, right? You can see that. First off, I guess what we should say is line 233 or line 232. We must have started beginning. We set up the data stack. I told you before that the SP pointer, normally used for subroutines and stuff, is being used by Mint for its data operations, right?
Yes.
So that's the first thing. Then once it's done that, we then call initialize, and initialize is a routine which is located somewhere which sets up a bunch of Mint related things. We can take a look at it, but let's just move on. We'll come back to the initializing Mint later. Now, this is an interesting routine, which I think is cool. Is call. Yeah, see how it's a call to this routine called print string. Yep. And then it's got this .c string. It's actually got a string, a null terminated string has been defined in the space just behind the call. And what it does is that if you put data immediately after a call, you could get yourself into trouble, because the call is going to go off and do something, and then it's going to come back and it's going to start executing data.
And it thinks Mint v.1.1 is data.
Yeah, and you wouldn't want that to happen. But
why is this cool?
But this is cool because this routine print string, it doesn't just return to the line 235 and start executing data. What it does is it pulls the return address off the stack and uses that as the start of the string that it's going to print. So it goes to the print string routine. The first thing it says is, well, what's the address of the string? And so it just grabs whatever's on the top of the stack, and which is the return address, and it says that's the start of the string.
But we didn't put it on the stack yet. It's occurred afterwards.
Yeah, but that's the point. By doing call at 234, right? What does call do? Call takes the current state of the program counter and puts it on the stack. And what it's doing is it returns the address of line 235. It puts the address of line 235 onto the stack. The line 235. Obviously, that's not the address, but you know what I mean. So it puts the address of whatever's at line 235. And then it calls this routine with this address being the return address, which is the start of the string. It then prints the text that's at that address. And then when it comes to a null, it gets past that, and then it gets that
program counter back.
And then it puts it back on the stack and then returns. And it will return to line 237. It will basically jump over the string.
Pretty neat.
Yeah, so it means that you can define a string in exactly where you want to use it rather than defining it somewhere else.
So that means you have to add some bytes for the program counter to skip over.
Yes, you have to
push a value plus the skip over.
That's right. Yeah. So the length of the string, because we know that it's a variable length string, we wait for the null, and then that we now have the address of line 237.
So this
which is
print string measures this.
Yeah, exactly. That's why it's cool. That's why I like it. And so eventually it will return us to the next thing, which is 237. That's where we'll return to. So then it calls prompt, and prompt will just print a greater than symbol followed by a space. That's all prompt is. And BC, this is the interpreter. So BC is loaded with the tib, right? Which is a buffer, the text input buffer. It's obviously loads it with 0, the offset into the tib of 0. And what it's going to do is it's going to, and I don't know whether we need to go, well, I think we'll do a quick pass over this because, and we'll go into it, but all this is doing is it's reading characters from the keyboard and deciding whether to put them into the tib. And when the user hits enter, it will then execute what's in the tib. Okay.
So it's number or command.
Yeah.
Decide if it's a number or command.
Yeah, it will decide if it's a yes. Yeah. It will decide whether it's a character that goes into the tib or whether it should be executed immediately. So it decides whether it's a letter or a number, a character, or a control key. That's probably the best way to think about it. So a control key like backspace or control L will interrupt this thing. Does that make sense?
Yes, it does.
Yeah. So okay. So you're typing. Okay. Yeah. So you're typing
a three-way branch.
Sort of thing. Yeah.
Okay.
So BC is set up to point to the beginning of the tib. It then stores that into a variable called tib pointer, just for program control. It then needs to work out the nesting level. This is a bit of a sophisticated or problematic thing, which is to say that when you're reading in input and you come across a open parentheses, then the line cannot be ended until the person has typed a close parentheses because they've started a nested thing, right? So when you're typing into this thing and you go, 100 open parentheses and then you hit enter, it's not going to execute because it's not a complete line.
In other words, expect more input.
Expects more input. So what we have is a nesting.
It could be another bracket.
Yeah, you can keep
another
going.
And another, and it's going to be
exactly. So the register E, the E register, is used to store the nesting value, and the nesting value has to be 0 before it's allowed to execute. And so I just thought I'd mention what the E register is doing in that context. And sometimes you have to save this pointer into this offset into the tib. BC, there's a few details. We might have to sort of keep going, but it's calling the nesting operator and it's updating I'm just trying to read what's going on here, but basically it's updating the nesting.
So these interpretation levels, this is like the broad flowchart of how Mint works.
Yeah.
Okay.
So what it's doing, where's the call to the input? Just trying to work out load A from HL. So, there's been a character somehow put into the tib. We're looking at A, then we increment HL, we decrement BC. What it's doing, it's calculating the nesting value, and then it moves on. It says, is the count 0? I think it's got to do with this, if not, loop around. I'm going to have to go deeper into this, but
why would you increment and decrement? That's weird.
Yeah, I'm not sure.
Hang on, the HL
Oh,
and
no,
BC,
no,
two
it's
different things.
we're decrementing the count of the characters in the tib, and I think
the pointer's increasing.
Yeah, and the count is decreasing. I can't quite remember why the count is
Because
decreasing.
you've only allocated, was it 80 or something?
Yeah. There's a limit to it. But anyway, so I'm not explaining this very well, but let's scroll down a little bit further down to 268. What it's doing is it's calling a routine, which is calling the bitbang routine or the 6850 routine to get a character from the keyboard.
Is that why it says
double clicks?
268. Is that because it's weight here? Weight for a character. Okay.
Yeah, so it's getting a character from the input. It then compares it with a space, which is hexadecimal 20. It's not from a port, it's from the serial input, but you can call that a port, but from serial input. Anyway, compare with space. Okay, so we compare with space, and then if it's less than a space, then it's a non-printable control character. If it's, so you can see that it says if it doesn't have a carry, that indicates that it is space or higher, right? Yeah, greater than or equal to space.
So if it equals, then what do we do?
It will still not have a carry if it's equal, but if it's below 20, then the carry will be set, which is effectively like a negative sign has been triggered. So when you see a carry, it's because of two's complement. It basically indicates that you're trying to subtract a bigger object from a smaller object. It will throw the carry will go high. So that's one of those slightly tricky things about Z80 programming.
So if you load 20, set carry.
Yep.
Okay. Which is a flag that we use to indicate
that it's below 20, negative,
Oh, okay. Set carry flag. Okay,
yes, you're trying to subtract 20 from the character, and if you get a carry flag, it means the character was less than 20.
Is this something to do with the beginning of an asynchronous frame of 8 bits? The space is where it begins, like a start bit or something.
Well, I don't know about asynchronous frames, but definitely the space character starts at 20, and then everything before that is a control character. So now that in line 271, we're dealing with control characters, okay? So it compares against null, 0, and that's actually seeing whether or not it's at the end of a string. I think we don't, yeah. So it will jump out if that's the case. But that occurs rarely. Like you're not going to see nulls normally in this context. So go to 273 instead, which is it a carriage return? And that's the symbol in the assembler to represent ASCII 13. I could have just compared against 13, right? And if it is a carriage return, then it indicates that we want to execute it. We want to execute the line that we've been working on.
So compare true, then jump relative to Z.
Yeah. If that's true, jump to weight char 3, which is a level which is further down. If it's anything else, then it's a control key. And so I'm using the word macro in this context, but it's a control code. So anything else, yeah,
it's a macro.
Yeah, or a control code, maybe makes more sense. Call it control code. Control key, yeah. Okay, as long as you know what I'm talking about there. So you can see what it's doing is it's looking up the control codes and it's using the value that's in the A register to look up the address of the particular control code. So if it was, for example, control H, then A would have the value 8.
You mean the accumulator?
Yeah, the accumulator.
Oh.
And it compares with the HL contains the table. So we add A to the least significant byte of HL, which is L.
Yeah.
And then we put it back into L. And then because H is already correct, we just then load the value into E.
Is that right? No.
No, it's not. We're getting the least significant byte of HL, which is L. Well, we're getting the least significant byte of the control codes and we're adding it to the ASCII of the key. I mean, we don't need to go into this, but the point is it's looking up the key in the table of control key macros. Okay. Yeah. So what we're doing...
Correct? Is that correct there?
It's not compare. I don't know where you got compare from.
Well, you add.
Adding is not comparing.
It's not. Oh, okay.
So what we're doing is we've got a table of control codes. You need to add the character to that table to find the control code definition in that table.
When did we put something into A?
That's what getchar line 268 does, is that it reads a character into A.
Oh, it's part of this. I didn't know that. Okay.
Yeah. I mean, it's not documented, so that's why you didn't.
Everything goes through A eventually.
Sooner or later, yeah, exactly.
Yeah.
And all it's doing is it's working out the address and then it's executing it. Okay. The way it does it is, you know that symbol we looked at before, /caret, which we talked about as being a go operation.
Yep.
It was it looks at the address on the stack and then it executes it. So what's happening earlier is that it gets the address and puts it into DE. This code 281, 282, let's just say that it finds the address of that macro, puts it into DE, pushes DE onto the stack, and then calls go on it. And go, and I'll explain what enter does in a minute. It executes a piece of mint, and the mint is a go operation, and it's reading the stack. So the DE value is being read from the stack, and it's jumping to that. Okay. So it's a little bit tricky. What's happening here is that you did a carriage, say you did a backspace, and what it does is it finds the backspace mint routine, gets the address of it, pushes it onto the stack, then it jumps into a mint. At 284, it's basically saying execute a piece of mint code. And at 285 is a piece of mint code. And it's basically saying get whatever's on the stack and execute it. And it might seem a bit weird that I've actually jumped into mint to do this. So I've actually jumped right into it at this point, and it shows you how you can mix mint with machine code. So all you need to do is have this function call enter, and then you put a null terminated string after it, and you can put all the mint you like into that string. When it finally comes to a null, which is the end of the string, it will jump back out again. So it's very similar to that print string routine I was explaining to you earlier.
Yeah. So you can write all your code in a back to front manner doing this.
Yeah, you could. You could put as much mint as you like into your machine code.
I guess in the humor section of your write-up, you can make some jokes like this.
Yeah,
that'd be crazy.
Yeah. I mean, it does your head in, but it's powerful, and it means you can suddenly get all of these extra features in your machine code with even if you're not using Mint in any other way, you could still just use Mint as
And we
a
can
sort of,
both fourth can't do this. Ha ha ha.
yeah, it's not as easy in fourth. You can do it, but it's not quite as, you know,
Not as
it's similar.
elegant as beautiful Mint.
It's not as elegant as Mint in that
No.
case. Yeah, you
Love
can
it.
definitely do it in fourth, but because fourth is a compiler, it's a little bit. You'd have to do a compilation followed by an interpretation. Whereas in Mint, your source is your compile. There's no compilation. Your source is your execution.
Yeah.
And then so that's all it's done is it's executed that macro. So if you've done Control H, it would have executed that macro and it would have come back. And that would have done a backspace. Okay, so I think we can move on. This is really just reading input from the user at this point. And we need to eventually get to the point where they've done a carriage return. And you can sort of see we get down to wait for, let's just skip on and just say that, okay, 317, we have finally typed in a line of code. We've done backspaces, we've done all sorts of tricks, and then we hit enter. And now we're ready to go to the dispatch routine. So now we're ready to get to line 320, 319, 320. So we are now at the start. Oh, and this is, okay, good point. 315, okay. 316 actually, 316. We now have entered into the tib a sentence, which is some Mint code. We are now going to hit enter on that code. And now we have got to this line 316. We're now going to put the start of the tib into BC again. So because now we're going to interpret what's in the tib as our program. Okay.
You decremented.
Yeah, that's because it's because I'm going to increment it immediately after. It's just a little routine. So I've had to decrement to make it work. It's just one of these things. But BC contains the start of the tib. Then I've moved it to just 1 byte before the tib. But let's keep going down. Now scroll down to the next bit where I increment again, right? So we've got 342. So that's a little bit of wasted code, but that was just a way.
Is that like you update the flags or something?
No, it's nothing. It's because we always want to increment at the start of before we do anything, because sometimes we don't want to increment. It's.
Oh, I see. It's an offset of an increment. Okay.
Yeah, sometimes we need to do that. So anyway, it's back to the start. It's the first character of. Yeah. We're now pointing to the first character of the tib, and as I say, BC is the instruction pointer.
Is that a mistake there?
No, that's number of bytes. I use this to calculate how big the routine is. So don't worry about moving those around. Don't even look at them. No. Just get rid of it. You're going to be doing it for all the code. It's all I've done is it gives me the ability to know how big the routines are, so I can move them around because we're trying to fit into 2K. It's definitely not for anybody else to use.
Yep.
All right. So what we do is we read the first character from the tib into A. Okay. So A now contains the first character, which let's say it's the number 1, right? Yeah. So that means A has now got hex 31, which is the ASCII for the number 1 in it. We would then get the opcodes table. We would load L with the ASCII that we've got, which is 31. And we would load H with the most significant byte of the address of the opcodes table.
We're uncompressing.
Yes, we're now going to look up and try and find the routine, which in this case is a number routine. So we basically are, HL now contains the address that we need to jump to, basically. And it's just a little bit complicated, but you can sort of see that it pulls the lowest, it then pulls the byte out of the opcodes table. It puts that into L. It then gets the most significant byte of the address to page 4 and puts that into H. So now H is equal to 04 and L is equal to the offset of the num routine, because that's what it would have been pointing to. And then on line 348, it jumps there, okay? So assuming it was a number, you could see it in the table that it would have jumped to the num routine. So if you search for num underscore, and I'm not just saying it because you've seen this before, and it can only jump 256 because of the way we're using least significant bit. The least significant byte has only it gets us to this point, but it didn't get us all the way to the routine we wanted to because it's in a different page. So that's unfortunate in this case. We have to do a double jump. We have to jump here and then we have to jump further. And it's just because
why don't you use JR instead then?
We use JR and everything, but like you can see, there's a lot of JRs in 776, 777. We use JRs where possible, but num is just too far away.
Oh, okay.
So I had to use a long jump rather than a short jump. So
Okay.
if you search for num colon, you'll get there. Get rid of the semicolon and get rid of the underscore too. And colon, yeah, that's it. And while I don't really want to go to the routine, what it's doing is that it knows it's a number, but it doesn't know what to do with it. So what it does is it rereads that the BC is still pointing at the number, which we know is 1, right? So A is loaded from what BC is pointing to. So now A contains the ASCII for the number 1. And then the rest of this routine will read characters from the input until it comes to a non-number. And when that happens, it will return. So while we could go into this, and this is, Ken did all of this. So when it just reads in numbers, and when it reaches a non-number, it will terminate. And we'll push the value of the number onto the stack. Okay, so you've done 1, you've typed 1 followed by a space. The end result will be the stack will now contain the number 1.
I don't see stack here. Where's the stack?
Good point. Let's see if we can work it out. Oh, there it is on 1295.
Oh, further down. There we go.
There we go. And the interesting thing is this routine does not return, right?
Oh.
It jumps to an address that was stored in IY. This is something that happened in the initialization, but
So
IY
index addressing.
Yeah, but we're just using it as an address because it's only 7 cycles to do this, whereas to jump can take significantly longer. Like if you jump to an absolute address, it might be 13 cycles or something. I can't remember. So this is 7 cycles. So it's actually just a quick jump. And what it does is it jumps back to the thing that reads the input. Okay, so let's just say that we've now got the number 1s pushed onto the stack, and we now jump back to the start of the interpreter. Yeah, which is if you just have to go back. I forget the name of it. It's called next. Yeah, you can search for the word next with a colon after it.
I've seen that word a lot in Force code.
Yes, exactly. It's because it's copied from that. So put a colon at the end to make it easier to find. There we go. So IY is given the value next, and that makes it easy to jump back to next. And this is so next is what happens after every step through the interpreter. Is we always jump to the next. It's the dispatch routine. That's what Ken wrote that. So you always want to jump to next after you've finished. You can see there's on line 363, there's an explicit call to next. There's a reason for that one, but you can see that's what you often want to do. And so if you ever see jump IY, then what it's doing is it means jump to next.
Okay.
in nearly every case. In nearly every case, there are some exceptions, but I won't go
So
into
this
that.
is a loop that's going from there back to here,
Yeah, yeah,
repeating
and
until now. Where does it fall out?
yeah, eventually it will fall out because what's happened with comp next is I've actually overridden this normal behavior and I rewrote
Oh,
IY.
here. This
Yeah,
test is here.
yeah.
Okay.
Basically, IY has been rewired. It's a funny trick that I used. So I think we should ignore that for now because it's one of those more advanced things.
Secret
So
sauce.
the secret sauce. So yeah. So next, where was the next? Where's next one? Sorry, I just need to.
It's
Yeah.
up here.
So yeah. So this routine
This gets
the
used a lot then. It
yeah,
spends a lot of time around this loop.
every second command or every
And if we compile the code, then we can get rid of this.
yes, and that's the main reason for compiling the code is it would
Well, how can we get
eliminate
rid
this.
of it now? Can't we? We can't get rid of it now, can we?
No, no, and that's the way the fourth style
So that's
virtual
the whole
machine
action of
works.
interpretation is you must
Yes,
look at your next so-called character, which tells you what to do.
exactly,
You can't
exactly.
assume that it's going to know.
That's right. And so, and it's that's the thing about interpreters is that interpreters are like you're creating a virtual machine code or a virtual computer, a virtual microprocessor. You've made a software version of a microprocessor which will then execute, and that's what you're doing here. It's
we couldn't bunch together a group between colon and semicolon. We couldn't bunch all these codes into one string and then basically just do jump, 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 jump through that string of
well, when you yes,
codes.
that's right.
That way you don't have to keep repeating this next thing. Just do them every command line.
Yeah, well, that would be considered compiled then if you're doing that.
Yeah,
and that would be largely what your result would be if you want to make a compiler. And I did a talk about this for fourth, where I did subroutine threaded fourth, and I got better performance, but it wasn't vastly better, and the code got bigger. So think about all those jumps.
That's dangerous. Yeah.
Jumps are 3 bytes, whereas a character is only 1, and you can end up with there's still overheads even to jumps. Okay. So every single idea you've had and will have, you have to run it against this test. Is it going to be faster, or is it going to be much bigger? And that's probably the trade-off is you can get more speed if you're willing to sacrifice size.
Fast is big, slow is small.
Yeah, that's right. And even and when you make it big, that slows it down too, because you've got to access like maybe 3 memory addresses instead of 1 memory address. Even if it's the CPU doing it. But I agree with you that you really want to. You don't want to have an interpreter. You want to have just let the Z80 just do what it does automatically. It's going to be faster than if you create a little Z80 machine which reads a byte, does a thing, reads a byte, does a thing.
What about preemptive? Like if you're going to run a exclamation mark or an @ symbol for store and retrieve, you preempt that there's going to be a number, so you put those two together always in your jump table or whatever it is.
Yeah, yes. And then it's about what. Yeah, I know what you're saying, because that's how machine code works, where you put immediate
values together. You put them close together. That's just a speed up thing anyway. That's just not required yet.
And I would invite you to think more about this, because it's basically I've been racking my brains about this stuff, but it's true that you can the model we're using is a stack. Stacks have got speed problems. If you can make a different virtual machine which doesn't use a stack all the time, but uses register assignment, then you can get things faster. But everything you do is going to be more complex.
As soon as you push it out to memory, you've sacrificed some steps.
Yeah, that's right.
Keep it inside the CPU. it'll run faster. Yeah.
But there's hardly any registers, so you've got to
I know.
sort of
Just have another stack inside the Z80. Oh, we have to re-engineer the silicon now.
That's why I wanted to add an extra stack to the Z80. That would be my idea of an improved.
Maybe there's one in there. We just don't know how to access it.
Well, the worst thing is that there could be one in there, and it'll be slower than doing it in memory, because everything about the Z80 is shit when it comes to this stuff.
And I heard that the Z80's accumulator is actually 4 bits, 2 pairs of 4 bits or something.
Yeah, the arithmetic logic unit is a 4-bit unit.
Crazy.
I've tried to use those shadow registers for everything. I've spent a lot of time working on that, and it's just no go. I've put a lot of effort. They're the most useless registers because they're slow as hell to access. And it's just an accident, really. Whatever they did in 1972, 73, we're still living with a sort of a screwed up design, but they're basically useless. Anyway, so scrolling down, you will see that we get to the starts of the actual commands. I think we can scroll past this init ops stuff and stop. And so enter was a routine you saw before. It was capitalized in the when it was called to run that little mint go routine earlier. That macro was being executed. But this is the routine for executing any piece of mint code.
So you go call. Imply that it's case sensitive.
Yeah, it's not case sensitive. And don't double click, by the way, just in case you want to change. Right. But yeah, you can make it uppercase. It's just I used uppercase enter earlier, and I just used lowercase down here.
It is good case sensitive, like you said.
No, it's not case sensitive. It converts everything to uppercase if you want to know what the assembler is doing. Okay. It doesn't care about case. The main thing is this piece of code executes a string, a C string that follows it. So you can do any piece of mint code. If you go call enter followed by a .c string, you put the code in there and it will execute. But that's just a general purpose routine that you can use to execute mint. We can talk about it later. CRLF is a routine to print character return followed by a line feed. It's using that print string trick I showed you before. And then there's a print string routine, and it's shown, and you can see it's a very short routine, but it's amazing, this routine, because you probably have not used 423 exchange HL with the top of the stack very often. That's probably not a routine. Like I only started using this opcode.
Sorry, what is this?
Yeah.
What?
It takes the value, which is the top of the stack, and then it swaps it with HL. So HL goes onto the top of the stack, and the contents on the top of the stack get put into HL.
Oh, it's a two-way swap.
Yeah, it's very handy. It's equivalent of like swapping in Mint. It's kind of like that, except it's swapping it with HL. It's very cool.
Wow. Well,
and then
it gives you a little bit of temporary extra space.
Yes. It's a really useful command.
Why don't we do that with all the registers?
Oh no, HL special, just like A. It's kind of a 16-bit A, really.
Okay.
And then we swap it back again afterwards, after we've printed it. So we call another routine called put string, which does the printing part of it, calling put char, and then it increments HL. By the end of that, it gets to the end of the string, and HL is pointing to the end of the string, which is a null. So we increment past that null, and HL now has the address we want to return back to. So let's put it back onto the top of the stack. And that's what EXSPHL is doing, is that it takes the top, it puts the HL back onto the top of the stack, and it takes the top of the stack and puts that back into HL. So it restores HL to whatever it was before.
In traffic, this is called an overtake.
Yeah, and then we call return, and return just jumps back to whatever was on the top of the stack.
That's
So
pretty
that's it.
cool.
So let's scroll past all this lookup ref and stuff like that. You don't need to, these are all been highly optimized, and get to the first command. So if you keep print des, print des is the first command. That's actually dot. But these are very low level. This is going to print the decimal number that's on the stack. And print hex does the same kind of stuff. So
what's happened here? This is weird.
Yeah, this is a routine which you search the internet, you're going to come across this routine. It's going to jump to print deck 1 with 10,000 is the highest digit in a decimal string. You know, like it's the fifth location in the string, the leftmost thing. Anyway, it's going to print each digit of the number you're printing.
What does it say? Fifth location of string.
Of decimal number.
Doesn't make any sense. I don't understand.
Well, look, you can see. Just look at the sequence: 10,000, 1,000, 100, 10, 1. What it's basic.
This is a hexadecimal number?
No, it's decimal.
That's decimal.
So we're printing the 10,000s, then we're printing the thousands, then we're printing the hundreds, then we're printing the tens, and then we're printing the ones. Does that make sense?
Okay.
Because we can only do 32,000 is the highest number we can.
So if I put this into this register, what does it look like?
If you put, well, the number that you're wanting to print is...
This will have 5 in it.
Yeah, so what was it called? No, it won't have 5. Let's say you're trying to print the number 10,000, okay? So DE contains decimal 10,000.
Okay.
It will then subtract, it will, so the number is currently sitting where? It's currently sitting
so this is a mask to call out each position of the character digit in a range of numbers.
Yep, that's it.
Okay, each you put it in, call, put it in, call, put it in, call.
So the number you're trying to print is in HL, right?
Yeah.
So if you had 10,000 in HL and then you put 10,000 minus 10,000 in DE, and then you jump to print deck, then it would load A with the character of 0 that's just before the 0 character, because we've got -1 added to the ASCII of 0. So whatever the character is just before 0 in ASCII is put into A. Then we increment A, so now it's going to equal the 0. It then adds HL to DE, so that will end up with 0 in there. And if there's a carry, if it's below that, then it will jump back to the loop. Oh, geez, I don't know. You know, you can work it out. I didn't write this routine.
Is this a textbook classic?
Yeah, it is. It is.
Okay, I'll look it up.
I invite you to find a better one, because this one prints leading zeros, which I don't like. And that's one thing that Mint does, which is just because we need a routine that strips off the leading zeros. But
okay,
let's not worry.
It's still okay. It's good.
Yeah. It's nice and small. I mean,
and when you get 4 or 5 digits, then you're reminded instantly you're looking at hex or decimal. Yeah. The wake-up call. Okay.
Yeah, that's certainly true. Although I still think variable length is better. Okay, so then the next routine, and I don't want to go into this either, which is print hex. Does a similar kind of formatting, but it prints.
Just before just what's this here? It's weird.
Well, you can see in the next line, 6, 4, 6, 7, it increments it. What it's really doing is it's loading A with the ASCII for 0.
Okay, string.
Yeah.
So this is a directive to the compiler: get the string of 0, ASCII of 0. Take 1 off it,
Yep.
and then shove it in there. Right. Okay.
And then we immediately increment it anyway. So that's the
I
reason.
should read the help files of this Z80. There's more in there than meets the eye.
Yeah. Oh yeah, yeah. You should definitely read Z80's manual. I read it all the time, or at least I've read it many times because it's necessary. So print hex is an equally fancy routine for printing hexadecimal. It's still quite short. Again, credit this all. All of this stuff is Ken's work. So just come through here. So we just take it for given that it's going to print a hexadecimal number. It's using two routines. Print hex 2 is down there. Yeah, it's there. And
Why are we
print
doing
hex
it
3.
twice? Oh.
Well, because every byte has two hexes. Has two hex digits.
Each digit is a byte. Okay, gotcha.
Yeah, something like that anyway.
Pop that.
Yeah. For the lower and for the it's for the higher and the lower.
Okay.
Yeah, but each routine then gets broken into two characters. Each byte gets broken into two characters. Anyway, let's scroll past this
You do the high
because
part and you do the low part.
yeah, these are just utilities. You can find them on the internet. These kind of things. So scroll past that. Now, the nesting routine, we don't need to go into any real detail, but it is probably the most sophisticated part of the parser because it works out how to balance things. So it's looking for square brackets, it's looking for open parentheses, it's looking for colons and waiting for semicolons. It's looking for backticks and it's counting backticks. Backticks need to come in pairs, right? So there's a lot of things that are used to work out whether the statement is balanced, and it's only when the register E gets to 0 that we've read in a balanced string which can
That
be
was
executed.
when we did a if then else where you bash two brackets together, a pair of them. That's something else.
It would work. It will count them and they'll still be balanced.
You know, like when you did this, like that.
Yeah.
That one up there.
Yeah. It's still balanced because it's open, which unbalances it, then closed, which rebalances it, then open, balance, unbalanced, and then closed, rebalanced. So the end result is it's balanced. It's only when you've got an open which doesn't have a close that it's balanced.
Okay.
That it's out of balance. So anyway, it's not a very long routine, but it wraps up all of the mint balance rules. And I'll let you sort of examine that at some other point, but the main thing is it's needed for so that we don't. I use it in a few places. Okay, so page 4, here we go, finally. So the first thing you need to know is 544, align 100 hex. So a line basically says, doesn't matter what you're up to, I want you to snap to the nearest 100 byte page boundary. So if there's any space between 539 and 544,
put
545,
in it.
yeah, it'll leave it as, it'll just jump ahead and it will start assembling at the next point.
Okay.
And it's very important because we're using these 8-bit, we're only using a 1 byte addresses because the table is a byte table.
Yeah. And
we have to break these things into pages. And that's why you sometimes see jumps because we can't always fit everything in a page.
Yeah.
But you can see here, we've got in page 4, you've got all the basics of mint, which is and, or, exclusive, or, invert, add, again, which is the closing of a loop, array definition, call, which is execute a command.
This is closing a loop.
Yep, that's right. So we've got call, we've got dot, we've got h dot, which is a comma, we've got drop, we've got dupe. ETX is a little special command I use in the interpreter. You can ignore it for now.
Does it do anything for us?
It's only used by the parser, so you don't need to know about it. But it's a command that basically says go back and complete execution. It's that kind of thing. End of text, it's an ASCII command, but don't worry about it. Exit is used. forget where it's used. I'll have to go back and think about that. Fetch, you already know. Hex is going to read the input stream for hexadecimal numbers. Key is going to ask for a key. You can see it's using call getchar. Yeah,
Yep.
that's that, and that one you know how that works because getchar is going after the bitbang input.
Right.
Mul is multiply. Nop is do nothing. See how it just jumps to next?
Yeah.
That's all you need to know is every function ends with a jump to next. And it probably should have been a jump to IY. So you can see on line 6, 7, 8, it's jump IY. That's the same thing.
If I put IY here, it'd be fine.
Yeah, no, it won't.
Like
Because
that.
yeah, you could, but it would break array definitions because arrays, what I do with arrays is I do a trick where I completely hack the next system. So ignore that. Don't do it. All I'm just going to say is probably shouldn't do that. So don't change jump next to jump IY, but you would be right. It would work, but there would be a few things that would break. Over is for moving the stack around. Return is a semicolon. Rot is rotate. SHL is just shift left on 694. And SHR is shift right. Store is exclamation mark. Swap is dollar. Sub is subtract. Neg is negate.
Well, we got two subs here.
Because I'm probably jumping into there as a way of, because there'll be some other routine that uses it, and all I'm doing is I'm jumping into the middle of here because I'm wanting to save bytes. So it would be just, yeah, you can see it on line 737, jump sub 2.
So this group does two things. You just split them in half.
Yeah, yeah.
Gotcha, yeah.
So negate is related to subtract. That's why I'm using the subtract routine to do negate.
Yeah.
I'm negating from 0. I'm subtracting something from 0. It's the same as negating it, right?
Yeah.
There's another way of doing 2's complement, but that is actually probably the fastest way to do it, is to subtract something from 0.
If you do sub, does that mean you have to complete to that point, or you can stop here?
No, you have to complete to the jump IY.
All right. And this one,
it will jump to sub 2.
like there, and exits there, exits there.
Yeah,
right.
Exactly.
And
so
this one,
EQ is equate, so that's the equals, and just compares again. It compares to see whether the
exits from that routine left.
Yeah, it has to jump to less, which is probably further down. There it is.
Yep.
Yeah, yes, and you can see greater than, less than, compare, equal, less, etc. So
very tiny routines. They're so small.
Yeah, yeah.
Wow.
And they rely on, and sometimes they fall through from one to the next, because we're trying to make it as small as possible.
Yep.
So var is look up the variable that you've just, so if you put lowercase a, it would look up lowercase a in the variable table, and it would put the address of the variable a onto the stack. You would then need to use fetch to get the content of variable a. If you know
right, that's right.
Yeah,
you'll have a pop HL for that then.
Yeah, well, it's yeah. You can have a look at fetch. If you went up to fetch, actually scroll up, you should be able to find fetch. It should be in this group somewhere. There it is. So pop HL takes the top of the data stack.
Yeah.
It then treats it as a pointer. It loads E with the lower least significant byte. It increments HL, and then it loads D with the other one, and then it just pushes DE onto the stack. And that's
what will process that later? Something will print it out, will it?
Nothing will process it until you decide to process it. It just pushes it onto the stack.
So this stack is the same as the mint stack. Okay.
Yeah. That's what I mean by we're using the machine code stack.
Same thing.
For the data stack.
Efficient.
Yeah, it's very efficient. Okay, so scroll back up a little. Okay, Alt. Yeah. Yeah. We're now getting into page 5 primitives, which, oh yeah, okay. So not everything can fit into page 4 because page 4 is only 256 bytes. And so anything that can't fit in there, I jump to it. And so I jump into page 5. And this is a scheme that, again, this is Ken's initial take on this whole thing was this scheme. It's really good. But basically everything that you, actually originally this came from Peter Chikaki, but basically you try and fit as much as you can into one page of memory, and anything that you can't, this is Ken's idea, you would jump out and go to the following page. So you do another jump to the page that's just after it for anything that didn't fit. And so you can see that we have Alt, which is the backslash command, is called Alt. So when you do a slash, it goes here, and then Alt it's got its own, it then reads the next character and does something with it. So let's not go into Alt right now, but that's what Alt is for. Then str is for printing a string. And you can see that what it does is it just keeps printing and looks for a closing tick, back tick. And otherwise it just prints. It's just a loop, and it just goes through and prints until it sees a closing back tick.
Well, that executes itself. Okay.
Yeah.
Array not end. Call the next character and keep going.
Yeah.
Jump back to there. Okay.
Exactly. It's very straightforward.
So tidy. Wow.
It's cool. If I had invented it all, I'd be even prouder. But the point is, there's several things going on here. There's Forth. I'd implemented 2 versions of Forth by this point. Ken had built a really nice skeleton, the very first version of Mint, and was basically working his way through the commands. I came in and said, there's several things that Sandor's stable program does right with regard to looping and if statements and so on. And so I got involved, and we started expanding the language.
Sandor from Hungary. Yes.
Yeah.
He's the black curtain guy. He's worked behind the curtain.
Yeah. Well, you remember this because you said I'd like to convert this to Z80 about 2 years ago, right?
Yeah.
And I had more or less the same thought. And while this is not stable, and we actually would be worth doing stable as well, because I've come to appreciate more and more how good.
He doesn't like to comment anything.
Yeah, unfortunately, he's disappeared. I mean, you might still be able to contact him, but I can't. But
he disappeared. Oh.
Yeah, he's not in any of the groups now. Look, I think he just got sick of because people weren't really understanding what he was doing.
He kept printing those Christmas cards and calendars and stuff.
Exactly. Lots of those kinds of things. But I think, since then, the minimalist computing group has really appreciated what he's done. It's just he was just a little bit ahead of us. And
I saved everything he sent me. It was bombarding me with so much stuff I couldn't understand it. But I conversed with him in native Hungarian. He's very funny.
That's awesome.
He's more interested in social and humor. And then, he's basically done everything he's ever wanted to do in programming, I suppose. Not a challenge anymore.
Yeah, that's exactly right. And I made a JavaScript version of Stable, which is still running. You can play with it. I'll send it to you, the link. It's up and running. It's in a GitHub, but it's online. You can run it. And I mean, it's a great language. I couldn't get 100% of everything right because he was using a terminal while I was using a web browser, but it's very, very close. I got the full language anyway, and he kept trying it out and telling me where it was, if it went wrong. Anyway, so we're just looking at arrays and we're looking at strings. We can sort of scroll through this a little bit, but you sort of see how array start, array end, string start. And this is where we get to def, actually 836. Yeah, keep going. So this is a colon, right? This is what happens when you see a colon. Okay, so we've got a colon. BC is currently pointing to a colon. Let's increment BC. And let's read the character that is immediately after the colon and put that into A. Okay, so if you were trying to define colon capital A or colon capital B, whatever, the register A will now have that letter, and it also writes that letter into the v last def variable, which is useful for re-edit.
This is only the least significant byte then of BC.
Well, because we're only working in characters, Mint only
Yeah.
works in characters, right? So we're reading
Every time
in.
you do anything like this, a double register into a single, it chops off one half of it.
Yes, but no, not in this case. We're reading a
Oh.
byte from
Byte.
BC. So we're reading a byte that is being pointed to by BC into A.
Oh, right. Okay. This is just the full address. Okay.
Yeah, so we're reading in the, so we've just done colon. Now we're doing a letter. So let's say we're defining a routine at B, capital B. Then the register A now contains the letter capital B, right? It then stores that in V last def, which is just stores it in this memory address so that we can use that in our re-edit command, because it goes, what was the last letter you defined? And you say, oh, I did B. Okay, so we store B in there.
Oh, yeah.
Then what it does is it looks up the address of B in a table where all the letters are stored. And what it is, it's an array which has addresses that point to wherever we put the text of the command. Okay, because they're all different lengths. We don't know how long they're going to be.
Yeah.
So we don't just stick them all in the same table. We have a pointer in the table that points into the heap where so A, B, C, D, E, each one of them is a pointer, and those pointers point into the heap. Okay.
Yep.
And so we then get so we get the pointer, and then we look into the and then we're going to start. We get to where the heap pointer currently is, which is the first available free piece of memory. And we're now going to start copying the contents of the colon definition that's been entered into the heap. And then when we finish, we're going to move the heap pointer to the end. And what that means is
where is the heap?
Okay,
is
the
that
heap
the address
is
of the heap there?
Yeah, this is the pointer that points to the heap. So this is the /h variable.
Oh.
So what it means is that we're just going to copy everything that we're typing in that definition into the heap. And then we're going to move the heap pointer to after it.
So this is the copy part. You keep incrementing the counters.
Yeah, exactly. It's just read, copy, read, copy, read, copy, etc., until it gets to a semicolon, which you can see on 858.
858. How do we loop around this part here?
Well, obviously not there. It's not, the jump is further down. Look at there we go. Okay. So
then we go back to the top and do it again, right?
It's actually def 1. It jumps back to def 1. And it reads into A.
Like a breakout, right?
Yeah. And
the
semicolon is where it terminates.
Semicolon.
859. See?
And we jump out there. Okay.
We jump out. Yeah. And so that's all that routine does, is it basically copies the content, which is like a string ended with a semicolon, into the heap. And then it moves the heap pointer to after that so that it doesn't get overwritten. And it stores the pointer to that heap in the variable so that when you run the command B, capital B, it will execute this piece of code which is sitting in the heap.
Okay, and then when we're done with it, then we just get rid of it.
Well, you could definitely do that if you want to, but you
Deck
better be
B,
careful. Don't execute it after that. But yeah, you could easily set the command back to empty or to null, and it
Oh.
would stop executing if you didn't want it to execute anymore. But yeah, so that gives you an idea. So let's move on, scrolling, and we can just sort of see that we're actually not doing too badly because these commands are quicker to describe. Divide, we don't care how divide works. It's just Z80 routine. You can work that out. I invite you to study it. I didn't write it. Begin and end are interesting, but I don't know whether we want to go into them in too much detail. But you know how I was telling you how we use, after divide, so after div, scroll down, after div, we're not interested in div. Don't give a shit about div. Okay, begin, right. So begin is the start of a loop. And you know how I was telling you that loops are done using a loop stack? And that what we do with the loop stack is we push there are three items that get pushed onto the loop stack: the address that we loop back to, the limit, which means how many times we go through the loop, like 100, and the loop counter variable. There are three items, and you can see that begin is all about that. And
one of the members in the Tech One group did a write-up about this.
Using,
yeah,
I'm not completely sure, but that would have been Brian, I reckon.
Yeah, Brian.
Yeah, it's always Brian.
The train guy.
Yeah. Anyway, the loop routine is pretty long and it has a lot of things to deal with because, as you know, it's the if statement as well as the loop. But it's not too big. Yeah, it's a big one. But and now we're back at div. I don't know why we're looking at div. Why are we always looking at div? I don't give a shit about div. All right, there we go. So begin and again are related to loop. Scroll down. And now we're into page 6 primitives. Now, page 6 primitives are everything to do with slash in front of them. So I told you about alt before. Well, we got the implementation in page 5, but all it means is that everything to do with these slashes, they start with the letter A. So maybe they don't, but A not, and maybe they're not. Anyway, the main thing is that everything that starts with slash is implemented in page 6. So we've got stuff like byte arrays, C array def on 1016. Is an example of a byte array. C fetch, which you know is to get the byte value of an address. So that's slash fetch. Comments are slash. C store is slash exclamation mark, which we found was a bug earlier. Slash comma is an emit, which means print the ASCII character onto the stack. Scroll down a bit further. Some of these other ones.
Dot instead of slash comma.
Yeah, it could have been slash dot is for printing a string.
Oh, okay.
Slash comma is to print an ASCII character. Keep going, and then you can also see slash caret, which is the go. So, I mean, this could do with better comments, I have to say. It should be telling you that slash caret is this routine, go. You know that slash less than is import. So that 1091 is, I mean, this could be annotated, seriously, for sure. Import is 1091. That is slash less than. Yeah. And, we've got slash I and slash J. We've got slash $, we've got slash greater than.
and we've got slash curly brace, which is do with pushing and popping, which is R pop and R push. So I have to apologize for the lack of comments here. You can see them in the table, but you can see that I didn't show the equivalent mint command that you're getting, but it's there. So
For effort, nonetheless.
and anyway, we're nearly at the bottom, and now we're just getting into now see this one here, utils, 1070. These are all
1070.
yeah. Oh, sorry, 1170.
1170. Okay.
Sorry, apologies.
That's
This
right.
is a table of slash hash number. So slash hash 0 is execute the address and it executes machine code. Okay. Slash hash eret is a way to return. Yeah, it'd be hash slash 0, not 1. Yeah, 0. 0, yeah. No.
No?
I mean, yeah, okay, all right. If you want to do that, yeah, for sure. Okay, yeah, you could do it there. Yeah, slash hash, yeah. So that'll make it probably clearer how to use it. And then the same for all the others up to 7. So you can see exec return is being duplicated. Unloops, like some of these are old. I think I need to get rid of some of these things. Depth. So slash hash 3 returns the number of items on the data stack. It'll actually return
I've
a
used
number.
that. Yeah.
You've used it before, yeah.
Yeah.
Print stack is used for printing the stack. You can do that it's the same as Command P, Control P.
That's right.
Print the prompt, edit the definition, and I think adupe is just used for some testing reasons, which you can ignore. So that's the idea of the table of those numeric slash hash things, is they're kind of low level and didn't need to get their own letter of the alphabet. That's the main point. Letters are so scarce that I just didn't want to waste them on such specialized things like this. All right, scroll down. We're on to page 6, which is just the last remaining, page 7, in fact, last remaining remnants of a few routines here and there. And if you scroll, that looks a little out of date, that comment, because it's got a slash in front of the parentheses. But yeah, that one
Up there.
Yeah, I'd say that should go. But and that's would show you what it's going to print the stack. In fact, it doesn't have the parentheses in the real Mint, right? So print stack is actually a Mint routine. We've got call enter followed by a C string, which prints out that equals greater than prompt followed by space. Then it gets a, which is a variable, and it subtracts 2 from it. I can't go into the details because I can't remember much of it, but it's going to print the stack, basically. It will just print everything that's on the stack. And it will do it based on the base. So it'll do it in hexadecimal if you've done a command. If you do a Control B and switch from hex to decimal, when you do Control P, it will do it. It will print it in either hexadecimal or in decimal. But anyway, let's just move on. String definitions. There's some code there for defining a string. That's slash backtick. And then if you just scroll down a bit further, you can see that there's just some leftover bits of routine to handle the multiplication. Scroll a bit further, you can see there's stuff handling numbers. That's the num handling routine. Keep scrolling, we're nearly at the bottom. Hexadecimal handling. For printing a prompt, we've got a routine to do that. And for editing a definition, and for pushing and popping onto the return stack. Edit definition is the one that you use Control
J, Control E, Control E. Anyway, and that's it. That's the whole of Mint. That's everything.
That's it.
Yeah, we got to it.
That's it. The whole program's there. Wow. And it's midnight.
Yeah, how many hours is it? That's incredible, isn't it? That's a long video. But
and this is like a year's worth of work between 3 people. That's crazy.
Yeah, actually, it took even less time, but I think if you added all of the different other projects that led up to it, so learning how to do fourth, but I mean, Ken spent a couple of months in, I think June, July, thereabouts last year, fleshing out the first version of Mint. That I can't remember what month it was that he was doing it, and then I got involved in October from memory, and I dropped the fourth project that I was working on to work on this because the idea of doing a language in 2K. So actually it came together, I would say, more like 5 months in total.
Wow, it's impressive.
And yeah, I mean, of course, we're limited by what we can fit in. And now I'm kind of thinking that I'd like to do other slightly different language next time, but which is easier to read than
another language for the Tech One. Sure.
Of course, the Tech One never has enough languages. Yeah. No,
what other languages are there? There's nothing left.
Yeah, but I'm thinking. I'm thinking that the stack. I like the reverse Polish, but I don't like the stack manipulation instructions. So where I'm going with this is to have something closer to named parameters instead of finding out using rotate and duplicate and drop and all those commands. You just simply say, there are 3 arguments. They're called A, B, and C, and add A and B. Like, you go A, B,
like
plus.
basic.
Yeah, but it would still be reverse Polish because you would still need a stack for, it would still be a little bit reverse Polish, but it would be still pretty easy to use.
And you're promising all the power and the speed and the glory.
It has to be the same speed, but better syntax. Yeah. And what you were saying before about having multi-character commands is something I'm thinking about as well. So it's more just, anyway, these are just idle thoughts, but Mint can definitely evolve. Whether it's Mint or whether it gets a new name is the next question. But and I haven't really thought this through because, there are slow ways to do this, but in an interpreter, you don't have any luxuries. You don't have any way to compile things to make it faster. So it has to work fast as an interpreter. So anyway, just some ideas at the moment.
But when the scientists and the theologian get to the top of the mountain, they realize that assembler is the only way to do everything to please God.
Yeah, absolutely. Oh yeah, for sure. The 12 tablets were written in hey, did you ever read the book Snow Crash?
No.
Yeah.
It's fiction?
Yeah, it's science fiction. It's a cyberpunk thing. It was just, suddenly reminded me that this idea that the ancient language of the Middle East was like a machine code, and the first programmers programmed humans. Anyway, it's one of those funny ideas. I'm going to stop recording this session now because I'm going off into la la land.
I'll look up that book. Cool.
Yeah, it's a good one. It's an old one. It's pretty old. It's from the 90s. Anyway, I'm just going to stop the recording.
So you'll upload this to